Talking, Satichari. Okay. Hello, everybody. It's 104 people. 104 from 350. Where's the rest? Oh my God. Hi, Shvirag. Oh, I think I saw Yichi's name go by, but it went away. I'll put it back.
Professor, this is Den Staff. I need to check if the recording has been started. Just give me a couple of minutes.
Yeah, yeah, definitely. Take your time, okay? It was Yuchi, okay. Yuchi, Yash, Siddhi, Panchal. Hello. Hello, Prof. Hi, Yash. P always just this one letter. Hi, P. Shobit, Kaiway, Vaishnavi, Srinidhi, although Kenneth. Yeah, we'll just like bite time. What bird do you think this is? I made this bird on Friday.
Hello, Professor. Yeah,
Yes.
you can begin.
Oh, good. Okay, so I can begin. Yeah, it looks like a stork, right? Storks have like long feet, right? And they also have a much long beak. So not a stork, but keep guessing though. It's definitely what's called a waterfowl. No, it's not a chicken. It's actually a really tiny bird. and yeah, it's a lot like a pelican, but pelicans have a much bigger beak. This flies very, very, very far. This is a tiny bird, but then its migration is just wild. It flies across the US. This tiny little thing. We should make carberries. Perfect. Wow, Nathan Lee. It is an Arctic tern. Is there any sound? I hope so. Can you guys hear me? Okay, good. So Hamza, you might have to, I guess, restart your session. All right, so it's an Arctic tern. You can go look that up. Cool. These days we collect data on them. It's all about data. You could put tiny GPS receivers that have wireless transmission and then get their GPS coordinates when they fly across the US in real time per bird, maybe 1,000 birds, and then stream them to a database and actually watch them on your screen like a group migration. Biologists go crazy, ornithologists who study birds, they go crazy with this because just 10 years ago they could only dream of doing something like that, but now it's actually possible. Okay, check this out. We have a new font that happens to be called Ubuntu, an Ubuntu font, just like the Linux system. And then we have a golden yellow kind of color, the links. No data for you. It's a data Nazi. Okay, but there is data for you guys. And then here everybody is. You will actually start to like know them much more pretty soon because I'm gonna give you homework one, which really has to do with ER diagrams. So you need to create the template for a beautiful working database. If someone were to take your diagram and turn that into an actual database, it should work. You can even try it yourself. You could do some SQL after next class and see your design is actually valid. So no invalid designs, okay? That's when you lose points. Okay, hopefully you wouldn't lose points. It's easy. Today we need to, do this part. Okay, I'm gonna just jump right in. This notion of relations. So in the end, even though we talk about file systems that are not connected together, we talk about networks, we talk about hierarchies. But then the most general way to model anything, even in the NoSQL world, is actually this idea called a relation. It is forever. It's just a simple but brilliant idea. Many brilliant ideas are extremely simple, so you cannot come up with something simpler than that. That's what I'm going to tell you about. So the word relation, we went through some of this last week, but just to recap, the extra tab in your site always makes the other tabs open in new windows. Really? The extra tab, Professor, I missed something. Okay. I'll get to the tab in just a minute, okay, because it worries me. Instead of going through the slides, reading the chapter, no, 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 Kevin, you would actually lose out like crazy. I mean, you would always get more information if you go and read the chapter, right? But I tell you some things that are actually not in any chapters. And then more importantly, the exam, the midterm, and the final are based on what I say to you here and not from the book. Like, I never read the book myself, let's put it that way. So now you would be totally off if you do that. So please don't do that. So don't say instead of, you can say in addition to, if you want more, because we have no time to go through like 1,000 pages of textbook, right? No, you should absolutely check the slides. More than check the slides have just a few words. Listen to the audio video. So listen to what I say. That is really where everything is. Because I tell you things that are, easy to understand. They're not in the books. All right. A relation is simultaneously two different things. On the one hand, a relation is a relation between two different tables. That is mostly what we call a relation. That is why it's called entity relation diagram, because the two tables are called entities. Entity A, entity B, and then we have a relation between them. So here's one entity relating to a different entity, like one student taking many courses, and then one course being taken by many students. It's a many to many. So we call that a relation. On the other hand, a relation also is every cell in just one of those tables. So just take any table that has any number of rows and columns. We call this a relation also. This is also a relation. And then the reason is because this relation right here relates this row, maybe the student, to this major. So the student happens to have that major. Obviously, some other student also has that major, but that's a separate relation. So every cell is also called a relation. Okay, so two meanings for the word relation, but the meaning that we most of the time use is relation means the connection between individual entities. Okay, so that is all relation is, a logical view of data. And then, so going to this table idea, so I just now had a table, maybe I should have a table on the side when I talk. So the table on the side is all facts about a table. So what are all the different things that are true about a table, okay? What it is on the one hand, a table has like rows and columns. It's a two-dimensional bunch of rows and columns. Each table, each row is called a tuple because it's multiple values. We call it a tuple. It's a one entity occurrence because the whole thing is called entity set. An entity set is all the rows, all the students. So one student is called entity occurrence, like one object is the collection of all the objects. And then the columns are the class definition. Each table column is an attribute. So that is what you use to measure something about a student, something about a bird, something about a vegetable, something about a car. They're all columns. What do you want to collect? These are called features in machine learning. We call this a feature. So feature. So when you look at something, magically you start thinking about features. Like we might look at this browser, and then you might tell yourself, the browser has 3 tabs right now, like at least 1, 2, and the third one I can click on. Or you might say, there's numbers 1 to 8. So we call all these features in the world, okay? It's one of the problems in data modeling or in AI. Those features are not obvious. So when you see this browser, when I see this browser, we might be looking at 2 different things, but they're all features. Columns. Okay, so each intersection of a row and a column represents a single data value, which is also called a relation. All values in a column must be the same format. Okay, that is in a way obvious because columns are common to everybody. So if this is GPA, it's going to be everybody's GPA. Suddenly you will not see somebody's graduation date, okay? If this column was your last name, it'll be everybody's last name going down. If this column was your social security number, it'll be everybody's social security number. So columns will have the same data format. Each column has a specific range. GPA can only be between 0 and 5, but confusingly we call a range a domain. In math, the x-axis is called domain, y-axis is called range. Domains map to ranges. So here we confuse them, conflate them, and then call the range, call the domain into range. But that's how it is. And then this is key, right? If this was printed on a sheet of paper, and this is one student, this here is right one student. If I cut that student out with scissors and I glued it here, it's still the same student, nothing changes. Similarly, if this used to be a last name, if this used to be a first name, I don't like that. I want to move the last name. I want to grab all this last name and then move it right next to first name. Nothing will change. So the table remains the same when you cut out whole rows and whole columns, which means positional independence is there. It doesn't matter how this table is actually stored in disk because it doesn't matter at all. When you say entity, do you mean entity occurrence? When we say entity, we actually mean the entity set. Okay. Yes, the whole table is what we mean by entity. Entity occurrence is really row. Most commonly, we call it a row. Okay, order doesn't matter. And then each table must have an attribute. Okay, this is the key part of it. In every table, there must be at least one column where all the values are different from each other because that column is like an ID column that is the primary key. Sometimes one column, sometimes 2 columns together. That combination must be unique. You know all this, okay, so I won't spend a lot of time telling you, but that is key because otherwise it doesn't matter what all these other columns are. Imagine a table where 100% of all of this is identical. Everyone has the same advisor, same major, same GPA, same graduation date, same school, same every gosh darn thing. But the student ID or the first name, last name combination is different. So you would still say, wow, all these students have everything in common because they're still different students. If you make all these, or even 2 of them the same, then you're screwed because you don't know which row is what, okay? So that must be distinct, and we call them primary key columns or just key columns. Okay, so I'll speak more about keys now. So key is really the key idea because otherwise without keys, tables will not exist. So one or more columns that determine all the other attributes. So if you give me a student ID, I can go to the stars report and know everything about you academically. So key is used to ensure that every row is unique. These are all many ways of saying the same thing. Two rows cannot collapse, so 4 rows, 5 rows cannot collapse on top of each other. And then establishes relationships. So this key is also used for a different reason. One primary key can be somebody else's foreign key. So if this was your student ID right here, student ID column, then I can make a completely separate table here altogether where the primary key is something else. It might be how many people ate at the restaurant, 1, 2, 3, 4, 5. But then we're trying to find out what students ate at the restaurant. So then the student ID can go here. And so if you're 5 here, and then if you are 5 here, then we assume it's the same student, and then they ate on that particular day. If you go on some other day and then you eat again, then you are the same student that ate on that day. Meaning this is called the primary key in this table. In this other table, the same key has turned into what we call a foreign key. So keys are also used to, establish the so-called primary key, foreign key relationships. In fact, every time you draw a wire between tables, that wire actually is a primary key, foreign key connection. Okay, that is really what it is. All right. So again, one last time, this is the same as that. See, this line is the same as this line. So don't be confused. In this book, they say the same thing multiple times. All right. So one way or the other, the idea is that the primary key holds the whole table together, because without it, we don't have tables. We have collapsed data. Good. Then determination. So again, this is another way of saying what I already told you. The primary key's job, whether one column or not combination, is to determine all the other columns, which all depend on the primary key. So again, you don't need to tell me anything about you, but if I glance at your student ID card and I take a picture of it, I'll know all about you because I can log in. That is called determination. State in which knowing the value of one attribute, which is the key attribute, makes it possible to determine the value of all the non-keys. When we say another, it's every other column ever. Is the basis of establishing the role of a key. Yeah, so any column that behaves like it can be independent and used to identify, we just call it the key column. It's an important column based on the relationship between among the attributes. This is another way of saying all the non-primary key columns all have a relationship with the primary key column. It's almost like a function, okay? So the primary keys are like a function variable. See, like this. So supposing if I say, y or something equal to f of x, then it's almost like this is the primary key. This is the primary key, and then this is the non-primary key. So if you give me the primary key, I'll plug into the equation, go in the table, and find the non-primary key. But then in a table, there's not just one y, there are many y's, so to speak. So you can call all of them as y0, y1, y2, y3, y4, but there's only one x. So if you give me that one x, I can go and find all the other, dependent variables. So independent variable, dependent variable. Is it like a barcode? Yeah, absolutely, absolutely. There are so many examples. Good, very good. I'm going to ask you actually during the discussion, name me some, primary keys. Yeah, barcode is totally primary key. Every product has a unique barcode. The whole world, it's never shared. All right, so now you understand, right? So if the barcode, checker scans it, robs to go ping, and the barcode scans, and instantly the price, the discount, the manufacturer, when it was made, all kinds of things are in the database. That's called determination. Easy concept. They're all very easy concepts. Another slide says the exact same thing. This one says determinants, which are the primary keys. Determine, like function. Dependents, which are all these dependent, these columns, they're called dependents. So once again, determinant is that one. This is the table. And everybody else is simply called a dependent because they're all dependent on this one column value. Easy. Dependence has another name, functional dependence. We just like to use fancy words, so we call it functional dependence, but it is dependence. It means the value of one or more attributes, which is the primary key combination, determines the value of all the other attributes. So how many times do we say the same thing over and over, but you understand. And then primary keys are called determinants because they determine everybody else. Like these guys determine everybody else. And all the others become dependents, which is what I told you up here. Okay, so I hope you're not confused, right? I'm just going in circles, but that way you fully understand. Okay, this is an important, obvious, easy concept. When you have more than one column for a primary key, suppose you have 2 columns for a primary key, both those columns need to be a primary key for a reason. Suppose it's a student ID, right? We also don't need your last name. And somebody tells you, the primary key is student ID, comma, last name. Every time somebody asks about you, give them your student ID and your last name. That's actually a waste, because when somebody goes and logs in, there's a column that says type in the student ID. The last name is not necessary, okay? So when you have extraneous, superfluous, wasteful, redundant, extra, boring, unnecessary, needless columns, that is not full functional dependence. That is called partial functional dependence. It means you have extra wasted data. Take it away. Only keep the minimum necessary. When you have minimum necessary columns where every column is important, then we call it full functional dependence. So the rest of the columns are fully functionally dependent on every column in the primary key when you have more than one column. When you obviously have a single column primary key, this all just goes away because you obviously always have full functional dependence. So full functional dependence is a good thing. We strive for that. These days, none of this is a problem. No database ever in the world will accept duplicates of anything. Okay, so primary keys, when you have one column, two column, three columns, somebody makes sure that they're all unique. Okay, so again, what I told you is just in one more slide, functional dependency. Again, student ID becomes the determinant. So student ID here, here, here. It functionally fully determines last name, dependent, GPA, major, everything. If you want, you could do this, but this is the example I gave you, it's wasteful. You don't need to make this whole thing a primary key because this alone is really a primary key. So this shouldn't be there. Then you lose full functional dependency. Nobody in the real world does this. It's pretty silly because, it's unwanted. On the other hand, in a different university, they don't like to give out IDs to students. I think names are very cool. Then they might decide, let's make a last name, first name combination and hope that no two students have the same first last name. And, if that's true, then that combination serves as the determinant, and then it can determine everybody else. So you go back to full functional dependency, okay? And this will fall apart when two students show up with the same name. Then you have to do something weird like drop a letter from one of the names. You have to fake to make it work. Or you can use a middle initial. So last name, first name, middle initial. And we hope that no two people, that come into your school have all three, equal. Okay, so that is why, when you go to court and you testify, you put your hand on your chest and you take this oath. I swear to say nothing but the truth, the whole truth, and nothing but the truth. So truth is over here, okay? So this is all truth. This is the world of truth. These are all things that happened that you saw. Something bad happened, and it's all of these things you saw. This is everything else. Things that could be non-true, fake news, disinformation, misinformation, confusion. So when we say I, swear to, you tell the truth, it means the key should be the whole key. I need to use the whole key. First of all, I need to use the key. I shouldn't go and use something here. What I use should be the key, and it should not be a part of the key. So if I have first name, last name combination, just one column is not enough. I need both of them. So the key, the whole key, and nothing but the key. So I don't need extra. In other words, I shouldn't tell the truth what happened and confuse the jury by, adding some extra thing that didn't happen. So no extra stuff, okay? Likewise, no extra columns. We don't need no extra columns. Okay, so this means we just use the key. And this is a joke because, Ed Card invented like all of this. So the key, the whole key, and nothing but the key. So help me, God. That is your database swearing line. All right, so composite key. Again, what we have said so far with first name, last name combination, we call it a composite. Otherwise, we call it an atomic key, a single column, such as your student ID. When we use only one column for the ID or social security number, sometimes even a phone number or an email address, we think that those things are unique. So we call them singleton columns, or we call it atomic keys because you cannot break it apart. On the other hand, a composite key is a key that has more than one column, such as first name, last name. It's the most common example. And then, so when you have one column or many columns, those columns, they're just called key attributes. Like student ID is a key attribute, or first name, last name is a key attribute. Okay, this is the entity integrity. All that this means is the table has unique values, at least for the primary keys. In other words, no 2 rows or no 3 rows, no 4 rows are 100% identical. When that happens, such a table is said to have entity integrity. So every real table in the world that people use, they have 100% entity integrity. That means everything else can be totally the same, but then, this ID value here cannot be this ID value also. Because if that is true, then who is this person, who is that person, we don't know. And they become the same people. Okay, which they're not. Therefore, at least that primary key should be different for all the columns. Whether it's one column primary key or 2 column primary keys, then the combination should be unique in every single row. That should not be anywhere else. Then we call it entity integrity. Easy idea, right? Okay. So it's like saying the obvious. So we hope that every database in the world has every table that has entity integrity. Otherwise, we have serious problems. So now we can talk a little bit about different kinds of integrity. There's one more kind of integrity, but in the meanwhile, and the reason why we bring up nulls is because that other integrity might actually break. This referential integrity might break if there are null values. So that's a different way of saying nulls are not really good to have in a database. So nulls screw up calculations. When you do SQL queries, the null just means the cell has no value. There's a blank. I go to look up somebody's GPA, and all of a sudden the GPA is blank. Suppose I want the average GPA of thousands of students, and hundreds of students, for some reason, the GPA is all just blank. Not zero, that means they have failed everything, but there's no value, so we don't know what it is. Then when you find the average of all of them, it is not the proper average. We should carefully leave out the students and then, get like a different average. So nulls present all kinds of problems, okay? We don't store the word null. Null just means a blank cell. It means we don't know what it is. Not knowing what it is worse than putting in some default value, including zero. Yeah, nulls are like void, exactly. It's indeterminate, so we just don't know what is going on. We have no data. Sometimes we might know it later on. So I currently don't know what the temperature outside is, but if you give me 5 minutes, I'll go measure it and find out. So I can have a null for just a little bit, but I can have a null forever. If somewhere there's a column that says, how many alien, planets do we know, in every in every galaxy. So every single cell value, for every galaxy would have just null because we have zero idea. We'll never know. It's a permanent null. Okay, so null is just an absence of data, okay? So it means unknown, but then I know it, but it's at home. I'll call you and let you know, that sort of thing. Null can also mean that something is, not applicable. Like supposing, you hire people that only have a social security number. And then, somebody shows up and for some reason you desperately want to give them a job. It's illegal, as far as US government is concerned, but you want to hire them anyway. So then that is an inapplicable condition because you might, put some fake number there. And that's the same as null, or you would leave it null because that person does not have a social security number. So that's a inapplicable condition. Or you think this club should only have people that are like 18 years old or or more. For some reason you want to admit the 16-year-old person. So then when you put their birthday in there, the system might take it, but that's an inapplicable condition. So if we don't want nulls, do we replace them? It depends. Yeah, it doesn't depend on the one student asked, what do you replace nulls with? It depends on your business rule. Sometimes you can replace them with zeros or even just some default value. Okay, you're probably like a JavaScript person. So in JavaScript, null is actually, there's a variable that exists. It doesn't have a value. Undefined means the variable or the function definition or the object doesn't exist. JavaScript makes a definition, that distinction between these. So in database, we don't make a distinction between these, okay? So null, undefined are the same. It means, there's a problem with that column. Ideally, by the way, in every table in every part of the world, right, for no reason, you want null. Null is not a good thing ever. You want to not have null. So in the social media world, and everybody using the internet, what happened was so many columns for so many people started having nulls. Like, what is your alternate email address? What do you mean I only have one email address? What is your LAN telephone line? What do you mean I just have my smartphone? What is your cable TV ID? To hell with that, I have Netflix. So all these columns just go blank. Or what is your social security number? I'm not going to tell you that. So people refuse to give out information, or they don't have information. So too many nulls got in tables. That's why we have NoSQL. Okay, so where there's no tables at all, there's no columns, so that whole problem just vanishes. All right. When you have nulls, you have a notion called referential integrity. So let me then draw this diagram, okay? I'll go back to my student ID idea. So I had a student ID column here, and every student has student ID. Suppose this is now the list of all the sports that people play. So every single sport, or maybe like all the students who play sports. So every student who plays sports, 1, 2, 3, 4, 5, that's a nice primary key. And then there's like what type of sport, what skill does it take? But here comes the student ID. So if you play 4 sports, then your student ID called 4 can be in this port, it can be in this port, or it can also be in this port. Okay, so therefore you can repeat. So 5 can be here, 5 can also be here. Because this is the primary key, and now this is called the foreign key. Because it sets its own primary key, some other primary key. Okay, so then foreign keys are supposed to point to primary keys. Because supposing you want this person to go on a tournament, if you want them to go play, against a team like out of state, you want them to travel. The first thing that they do is call the professors and say, do you have permission for the student to travel? So before you contact the professor, you need to know like what the department is, right? So you got to go look up the student's academic information and then call the department, find out what courses they're taking, all that stuff. So therefore, it's notion of foreign key having a pointer towards the primary key. What could happen is that for some reason, if this student like leaves the university and then this database for some reason this table is not updated, then you might be looking for a student who doesn't exist. Okay, literally the pointer is pointing to like a null value. If you try to access the object, your program would crash. Okay, it's a null pointer pointing to a non-existent address. Imagine these addresses, these are pointers holding addresses. Such a situation is called referential integrity violation. Conversely, referential integrity presence means every time you have a foreign key, it will have a corresponding primary key. So you can always look up what these are. Okay, that idea is called referential integrity. Once again, in many real-world tables, automatically we have referential integrity, because what can happen is these days there's something called cascade delete. So we set it up in SQL such that if this goes away, then the system automatically looks at all the other tables where there's a primary key and there's a foreign key and looks for the student and deletes like all of them, or at least puts null so that the 5 is not there anymore. Okay. If a key is not present deleted, then would it be null or garbage value? It'll be garbage value, meaning, if you leave the 5 there, then it's a null pointer literally, right? As good as, an invalid row. But if you delete that, then we don't know what it is. Meaning if you put null in it, then it's garbage. So the best thing to do is just basically erase this whole row so that the problem goes away. Okay. So if that happens, if you're pointing to nothing, it's called referential integrity violation. Okay, so entity integrity always is only about one table. Referential integrity involves 2 different tables because you're talking about a pointer from one column to another column. Easy, right? So don't allow invalid pointers. Think of this as a, like a pointer array, and then everything is here as an address, and think of every row here as an address. So you should not point to an address that is not there. In C++, your program would crash. All right, unless you look for it and tap it. Okay, so then what kind of keys exist? It's like a fun little simple slide. Before we get to some column that we call a primary key, maybe there might be choices for so many other columns to be a primary key also. For a student, why have a student ID? Maybe I should use the first name and the last name combination also as a primary key. So there could be lots of choices for what could be a primary key, okay? So imagine this, the world of all the choices for primary keys. So we call it a super key. It is simply a combination of attributes that uniquely define each row in a table. So it can be more than one. So a super key could actually be, on the one hand, student ID. On the other hand, it can also be the first name, last name combination. So we call many of those, right, super keys. But then super keys can also include garbage. You can have something like student ID and last name, student ID and first name. I told you these are useless, right? But technically, they could also be keys. They're bad keys, but they could be keys. So any such combination of a whole bunch of them together, they're all called super keys. Because you could pick any one of them. You can pick student ID, GPA, and it'll be a weird key, but it still work. So we call it a super key. But you look at the super keys one by one and you say, no, that's bad, we probably shouldn't use names. We're left with one, right? Yeah, exactly. No, the superset of all types of primary keys, possible primary keys. Yeah, you call it a super key. Then you pick one of them, and that is called a candidate key. Okay, so a candidate key, a candidate key would be you throw away all the junk and you only keep the good ones. So the good ones are the ones we'll eventually pick something from. Okay, so I'll tell you again, a super key can contain good primary key sets, like for example, student ID, first name, last name, but also bad ones like student ID, first name and last name, student ID, advisor's name, last name, first name, graduation date, like weird things. All of those are called super keys. But you throw away the ones that don't make any sense. You only keep the ones where when it is one, you totally need it. When you have two, you totally need both of them, like full functional dependence. When you have that set, that is called a candidate key, because this can be a candidate, this can also be a candidate. So having referential integrity means 2 columns shouldn't have any nulls. Having referential integrity means any foreign key value, every foreign key value in some table should be able to have a corresponding primary key. We should be able to always look up what this is in the primary key. That is called referential integrity. Can you explain why student ID plus last name is bad primary key? Because we don't need last name. Student ID alone is enough. The last name is wasteful. We don't want to waste columns on primary keys. So it's considered bad. Bad meaning bad design. It'll clearly work, but in secret, the system throws away the last name. So why even bother to ask somebody? A super key is primary key plus any other attributes. A super key really, yeah, exactly. A super key is possible primary keys plus any other attributes. Because there could be more than one, right? Okay, so these are all super keys. Student ID is a super key. First name, last name is also a super key. Student ID, GPA is also a super key. First name, last name, your school, like Viterbi, school name is also a super key. So all of these are super keys. Any one of them would work, technically speaking, right? When you say a combination, do we consider null as a value? No, there's no concept of null at all. I'm talking about column combinations. See, for a student, you collect many columns, right? You have a student ID column, first name, last name column, GPA column, advisor's name, graduation date, um, thesis title, anything at all, undergraduate GPA, undergraduate school's name, right? On and on and on. So that is what I mean by all these extra attributes. So you can consider any combination of columns as long as the combination is unique. That qualifies as a super key. Because student ID is unique, first name, last name is unique. That's all you need. But if I add one more, that is also a valid primary key, but we don't need that. Therefore, such useless primary keys, so to speak, are called super keys. So super key is basically, like a superset of all of these. So a super key need not always, no, a super key will always contain at least a primary key. Think of a super key as greater than or equal to primary key, okay? Greater than or equal to many primary keys. So isn't first name and last name by itself not a super key? Well, super key is a set. So as the set can have many elements. And yes, first name, last name can be one of them, sure. So the answer to your question is yes, it can be. Any more questions? I like all these. Yeah, well, in some school, if they think that first name, last name is enough, because we have not made the determination yet, okay? We didn't pick anything. Exactly like a composite key, correct. So a composite key can also be a super key. So everything that you're asking is all true, okay? Because the next thing would make it clear. Then we throw away the ones that make no sense, meaning why have first name, last name, and a GPA? It's weird. Why have all these? Why have a student ID and GPA? That is weird. So then you end up with a smaller list where either this can work or this can work, or maybe something else can work, So then those are called candidate keys because you're going to select one actual primary key from the set of candidates. So candidates are useful super keys. Composite plus primary equal to, no, not really. Because a composite can also be a primary. Wow. I'm going to start over because, I actually assume that a lot of people know this, right? I don't want to rush it at all. We could be a little late, you guys, okay? So I can even start SQL not even next week. So I'm not going to worry about it. We're going to get this right, okay? Because these questions, tell me, that you don't understand, but it's totally okay. It's more important to understand than to finish all the slides. Okay, so look, this is GPA. This is your advisor's name. This is your department. This is your graduation date. This is your student ID. This is your first name. This is your last name. What we mean by a super key is this. Yeah, it's okay. Don't worry about it. No blames. I'm not mad. I'm not disappointed. I want to do it right for everybody. Okay, so a super key is any combination of these columns where the values are going to be unique that sets every single row apart, because that is ultimately what we're going for. Okay, so any of those combination of columns can be called a super key. Here are some examples. The student ID is definitely a part of a super key because a student ID clearly works because every student has a different ID. If we assume that first name, last names can also be unique, they'll never be the same for two students. That combination can also potentially work as a good primary key. So we call it a super key. In fact, in this example, those are the only really useful super keys. Because if you pick this, then every column is unique. If you pick this, every column of this and this is unique. We call those candidates, by the way. So then this set eventually is going to become what is called the candidate key. But before we go from super key to candidate key, somebody might suggest more things just to, confuse people. But one of those might be student ID and GPA. But we think this is weird because for this we don't need the GPA, because for many students GPA is going to be the same. So why even have that? On the other hand, for every student ID would be different, right? So technically, if somebody picks this and makes this a primary key in a table, everything would work, the SQL would all work. But then we think this is needless, so such things we throw away, but they can still be part of the super key. So super key is anything that makes sense, that could actually work. So student ID first name is also a super key. Student ID graduation date is also a super key. So super key is basically anything that works. A candidate is exactly correct. Exactly is correct. Okay, so they're all super keys. Next, what we do is we throw away all the useless suggestions. So why did you even suggest that? Weird. We can now pick from one of those. So like Jack is saying, those are called candidate keys. That is the difference. From the candidate keys, you make one more determination and you say, one day we're going to be sad if we pick this, we're going to be sorry. So let's not do that. This is a much better idea. Let's go with that. That becomes the primary key. So we go from super key, which is a superset, down to a set of candidate keys, down to a primary key set, which is a membership of exactly one element, meaning only one of like that or that would become a primary key. Makes sense? So a candidate key, yeah, it sounds like anything can be a super key. No, anything cannot be a super key. For example, your advisor's name, comma, your graduation date cannot be a super key, because for many students, the combination will be the same, right? Same advisor, same graduation date. So it's not true that anything can be a super key, okay? It has to have something that makes it unique. Yeah, exactly. Jack Lee is correct. Read what Jack says. Yeah, exactly. Anything that can be used as a key can potentially be a super key. Yes, correct. Yeah, exactly. So anything that makes it unique, anything. Yeah, all of you are correct. Good. You guys got it. All right, so that is all this was, okay? So you go from super key to candidate to primary. These are just extra things that don't relate to, a little hierarchy here. A foreign key, you already know. A foreign key is a primary key in some other table, which has its own primary key. So in some other table, restaurants, so like all the different dishes that people eat. So if you go and eat enchilada, then your ID would go there. If you go and eat burritos, then your ID would go there. So then your student ID is over here, but that's now called the foreign key, because we don't need to care that they're all unique. They'll not be unique because you'll eat more than one dish, but it's unique here. So anything that is a primary key, when it is used somewhere else as a not primary key, we automatically call it a foreign key. Then what is the need for super key? The super key is just a conceptual exercise, just simply list every possible thing and you throw most of it away. What is the difference between candidate key and primary key? No, well, a candidate key could be, again, first name, last name. Like some school could pick this, or one designer would pick it, some other designer would pick it. But between those, this is a better choice, because we can always make sure that it's unique, this is up to us. But this is not up to us. Two different families name their kids the same, and then you're going to be sad, right? Yeah, exactly. So super keys for brainstorming. But to answer the candidate key question, you pick the best candidate key, like in an election, hopefully you vote for the best candidate. So candidates are, things that could be possible, but then in the end, only one of them wins. That's why I told you in here, the element membership is one, meaning there's only one primary key. There can be many candidate keys. There can be even more super keys. Clear? It's getting smaller and smaller. Net ID is a candidate key for colleges selling for student ID. Yeah, exactly. You can have all kinds of, IDs that we can use. In the US, social security number can easily be a primary key, for some schools. But if a foreign student comes along, then it wouldn't work. It means a super key is a set containing all combinations. Yeah, correct. A super key is a set containing a combination of all possible primary keys, along with, unfortunately, some columns that don't need to be there. Okay, but still will work, meaning useless columns. Yeah. So short answer to super keys, yes. Any more questions? Otherwise, we can move on. All right. So foreign key is easy. Foreign key is really a primary key, but in some other table where it's not a primary key. Secondary key is just a simple idea. Secondary key is like an alternate primary key. So what if somebody forgot the primary key? You don't remember all your primary keys. Can I use something else to ID you instead? That is now called a secondary key. It doesn't have the same guarantees, okay, as the primary key. For somebody, the secondary key might even be blank, and the system shouldn't care. A good example is Ralph's club card, your alternate your phone number. Most of us, don't remember a club card number. It's like waste, right? It's a big number. We just punch in a telephone number. So telephone number would be an example of a secondary key. Somebody might actually say, I'm not going to give you my telephone number. That's private. I'll carry my little card with me. So then they'll have an actual primary key. The secondary key would actually be blank, which is why that's totally okay. Okay, so secondary keys are not as ironclad as primary keys. They can be, null if you want. Or in the horrible case, two people actually purposely have different club IDs, right? But they put in the same phone number. So then, unfortunately, the system won't check. I actually don't know what will happen if you then go and put that, number in. But you will get points, and you will also get points. So the point is that the secondary key columns are not as rigorously checked as primary keys, but it's convenient. Yeah. You guys like net IDs, like that. Yeah. So anything that is a convenient key that is easy to remember, right? Anytime, again, in passwords, that's what they do. They actually ask you, oh, you forgot your password. Well, enter your mother's maiden name. Yeah, exactly. So secondary key need not be unique. You hope that it'll be unique, but no one checks for that. Yeah. Like with the phone number, right? Supposing you want club points, you'll hopefully put in your own phone number, not somebody else's phone number. So we just leave it up to individuals to, make sure the secondary key is unique. In reality, it is, but nobody checks. All right, moving on. But that. Why did you put that? That's funny. It's okay. So primary foreign keys are a subset of candidate keys, a subset of super keys. I showed that here. Super keys could be wasteful. So you just read this. It has extra columns. Okay, so simple compound composite. That's an easy concept. For primary keys, you only think about simple primary keys, composite primary keys. These are all about primary keys. Compound, key is really, even though it's like first name, last name might be an example, even though it is technically two different columns, you might still think of it as one compound attribute called name, and then the name is broken down into two. So it's a lot like this. But then you think, we take a composite and give one more name for it. So then we would call it a compound key, okay? So compound key it still has to be unique. The combination has to be unique. But then instead of calling it composite, we call it compound. Because again, a name can be two pieces, two composite pieces, two columns. But then we can even treat both columns as one column. Like say you have an object, called name, then the object can have one member called last name, one member called first name, which is really what keeps everything unique. But then the application program might actually call your name, or it might add your first name and last name together. So compound keys. Just a small distinction, but basically they are like composite keys. Natural keys are primary keys that are created from real world entities. So US, so we have social security numbers, and no two people, even dead people, have the exact same social security number. Those numbers are never, shared. Those numbers are not reused. So therefore, you would, if some table uses such a key as its primary key, then you would call it a natural key. So the USC starts demanding, everybody get a student ID, social security number before they join USC, because they want to use that as the primary key instead of a student ID. Then that student ID column would now be called a natural key because it naturally comes from somewhere else. Okay. Natural keys are actually dangerous because they give away information. It's the opposite of a blind key. As natural as all this sounds, it means someone can then look at your social security number and know what county issued that card for you, because all that is encoded. Or if the area codes make sense, then 818 area code, it means you're somewhere in the San Fernando Valley. I'll try to track you down. So therefore, we don't like natural keys, but they are always an option. Can a natural key be all the different forms? Yeah, they absolutely can be. Within many countries, your government ID, that'll be natural within that country. A compound is the same as composite in the sense it is made of more than one column, the combination of which needs to be unique. But we don't leave those two columns separate. We join them just conceptually with one more name. Okay, so say you have, again, t-shirts or something, right? And you want to make sure that every time you buy a t-shirt, I'll not buy the same t-shirt color that I already have. My goal is to collect every kind of t-shirt color. Then I can have a column where I can track like all my t-shirts, and the column can have three values, RGB. So every time I buy a new t-shirt, I want to make sure that RG and B are all separate, meaning I pick a new RGB value. But I don't like RGBs. I'll also have here something like a color name. So an RGB of, again, red 128, orange is, sorry, red 255, or green is 128, blue is 0. It's like a dark orange. So I might say the word dark orange. And the dark orange would then be a compound key. Because all that means is it is still made up of, individual keys, which are separate. But rather than call it RGB, I give it one more name for it. It's like one more level of indirection, okay? So the compound is exactly correct. The compound is composite. I don't know what you mean by fields being, don't worry about the fields, They're composite with like another name for it, that's all. Is student ID a natural key? Absolutely not. It's actually the opposite. A student ID is a blind key because if one student has this key, this ID, right? Suppose you have 4268 and now 118920. Then supposing another student is, suppose you got this, you stand in line at USC, wait, you go in the registrar's office to give you this card, they take your photograph. You see the next student going, okay? So when she comes out, you think that her number would be 1 and you would be wrong, okay? Because her number, the one that was standing right behind you, might be entirely different. So nobody can ever guess somebody else's number based on your number. It's totally random. They generate one more random 10-digit number. Thankfully, there are 10 raised to 10 combinations, right? So they'll check that random number to see if that is already some other student. If it is, generate one more. So they'll make sure they keep generating until they get a completely blind number and then give it to you. SS is somewhat random, somewhat not random. SS has a bunch of numbers, right? 3 digits, 2 digits, and 4 digits. So there's some identifying information in there. You should actually Google exactly what you asked me, okay? Google is social security number, not blind. Is it identifying? Yeah, so blind means we cannot tell what is what. On the other hand, if you have extra information in the key, then it's not blind. A lot of natural keys are not blind. Composite keys are unique, but compound may not be. Well, if the compound, yeah, you can say that. But because we actually really, the system only checks for composite, like in the RGB value, you only check for different RGB values. So maybe it is up to you to name all the colors different. Supposing there are 2 different RGB values, G is only slightly different. I might end up calling both of them deep red, so you're right. So maybe compound names, can be the same. But composite keys, the components of them, the pieces of them must be unique. Yeah, correct. In reality, you can make sure of this. When I put in color names, the system can just say, wow, you already used that color name. You can say like dark red, say something like that. Is a phone number a natural key? Yes, it is. If the phone number has, the area code, and then, the 3-digit number and the 4-digit number, they all tell you like what exchange. These days, you can ask for any phone number because of the virtual. But even 20 years ago, the phone number would tell somebody, like what part of the city you live in. And, they could come and try to find you and kill you, right? Bad. Yeah. So these days, it doesn't matter. Okay, I love all these questions about keys. I never thought there were so many questions. So a surrogate key, you can also call it a blind key. Just make a brand new unique key. So it's opposite again of natural. So don't use natural. Try and make non-identifying, aka blind keys, because those are the safest at all. A compound key must contain a foreign key. No, they're very, don't even talk about foreign keys, okay? A foreign key really is nothing at all. A foreign key means a primary key went somewhere else. So no, that's not true, okay? There's no connection between them. Compound just means, more than one column. So composite, compound. A GUID, yeah, exactly. So GUID, is based on like, number of seconds that have elapsed since like January 1st, 1970. But I want to make sure that Jack understands. Foreign key is really, you're talking about some other table. All of what we've said so far is only about one table. Only when you bring some other table in the picture, you start talking about foreign keys, okay? So foreign key is an entirely different idea, so it's not that. Okay, so I want to move on, okay? If you like keys, then there's a lot more that we can tell you about keys. Okay, so this tells you, again, all the things that I told you. What is composite, what's a natural key like this, social security number example. And then surrogate, candidate, primary, alternate, foreign, all of those. Alternate is also called secondary, okay? And then this is how the tables are related. So you can read this, just to get a little bit more knowledge about it, okay? Yeah, smart key is the same as like a natural key, where it has some extra information that, like a zip code, for example, is not a good key at all, because then people know where you live or where you were born. Okay, so now you understand. All right. So there's always more you can read, but okay, now about relations, because I want to tell you, how you actually do the relational algebra. Like what can you actually do with 2 tables? Like where does equal come from? We'll use the same example over and over. And the example is very simple. Imagine you're running a hardware store. So let's start here. In the hardware store, you usually don't see this. And when you search, this comes up. You search for a claw hammer, you search for a rat tail file. But in reality, the system has these combination of letters and numbers that are used to uniquely identify every single thing that the hardware store sells. There might be 2 different manufacturers, both make a rat tail file, but this manufacturer's ID was that a different manufacturer ID, what. So therefore, you want to make sure that the so-called product code is entirely unique. Again, it's blind. There's no connection between any of them. So that is the primary key, okay? These can all be the same. So product description usually different. Product price can definitely be the same for different products. Product on hand. When I walk up to the shelf, how many units would I see there? Sometimes it's called quantity on hand, QOH, product on hand. On hand means how many do I have right now? Most importantly, who made that? Supposing many people come to your claw hammer in your store and buy claw hammers and take it home, and they bang nails. But as they're banging the nail, the hammer head flies off because the handle is so badly made, right? So so there's a little hammer like right there, the hammer, and then this comes loose and the hammer goes and smacks somebody in the head. That happens to 100 people. They all bought the same claw hammer. They'll all come to a hardware store and say, "What the hell? Give me money back. I'm going to sue you." So then you would have to contact the manufacturer and say, well, "Why did you make defective products? We gotta send it all back. I'm gonna send all this back." Therefore, you need to know who the vendor is. Like, what is the email address? Where does it live? That one number is enough to look that up because you have a separate vendor table where every vendor has a code. Every manufacturer that makes hardware, they all have a unique code. And these things don't have to be unique. Like a purchasing manager, and then what is the phone number? What is the cell phone? What's the what? But that one number is like a little link between the tables. So if I know 232, I know who to call. I'm going to call Annalise and say, "Annalise, guess what? You're going to get all your stuff back. You're going to get sued." So therefore, that is enough, right? Therefore, this is the primary key in this table. It has become the foreign key in this table. That's all it is. Which is why I told you, suppose this manufacturer goes out of business, then we should be careful to remove all of these. Otherwise, you might think that you can call somebody and complain, but they're not in business anymore. So the whole notion of referential integrity. If this is deleted, hopefully that should also become null, and then you should get some warning message that says, "Sorry, we don't know who makes this anymore." All right, you guys. So that is the connection between them. Okay, a primary key, foreign key link. We'll use this link a lot to illustrate our points. Okay, so nulls. If you tell me if you want my single word advice for nulls, avoid. But in reality, you can have special values, secret values that programmers put in. 666 means you'll never know, so forget it. Don't even look for it. You can have these crazy schemes, from the old C programming, and put in any kind of weird values you want. In real world, people actually do that. We call them flags. Flags are special secret values that are documented, and the SQL programmer, knows what to do with flags. On the other hand, to make sure that nulls can never go in a column, you can make the whole column in such a way that the system will not accept a null value. If you try and put a null value, you'll get a red error that says, "Sorry, try again." In many web forms, you see that, okay, so if it asks you for a bunch of things and you say submit, it doesn't submit, you get a red warning that says four fields are missing because somebody went and flagged them as not null. So not null means you can never leave it null, it will not accept it. Further, I can also flag a column. You did this in SQL. With one more flag, check it out. It says, every value must be unique. A combination of not null and unique makes it possible for the column to be a primary key column. But primary keys automatically are always not null and unique. In fact, this combination, not null unique, is what makes anything a primary key column. But we have the choice as database designers to make any other column also be not null unique, such as an email address. So I have your student ID, but now I start to ask you for email addresses, and you shouldn't tell me I have no email address because I won't believe you. And further, I think that you would like to get your email, so your email address is unique. So you shouldn't try and give me your friend's email address because the system won't, accept that. So I can make the email column when people register to be not null and also unique. Okay. So then, for all practical purposes, we're basically forcing it to be some kind of an alternate primary key, just informally. So that's what those constraints can do. When the details are blind, why does some databases use encryption when saving? Yeah, sure. You don't want IDs to be lying around because if someday somebody has permission, you can write some SQL code to go and look up every single information about that ID. So you don't want to leave like raw IDs lying around. Yeah, good. Okay, so now we do the actual relational algebra, meaning what we do is we ask ourselves, what can we do with tables? What if tables are data types? Okay. So let's first ask some question. What if a dictionary is a data type? What language would you have? What language pretty much makes a dictionary, which is key value pairs, and designs a whole language pretty much to deal with key value pairs? Try again. Python obviously has a dictionary data type. None of these actually. No. Yeah, exactly. JavaScript. So in JavaScript, we'll talk about JSON a lot, right? It's all about those keys and values. Okay, it's all about the keys and values. So you might say JavaScript is basically built around JSON. If everything were to be a list, what language would you have? The whole language is about the list. Lisp and also Python. Okay. So, in other words, every language, picks some kind of a data structure and then builds the whole language around it. So now our fun for the next, like an hour is what if tables are data types? I have a table, some kind of data type, meaning say it's an integer. Then can I take a square root of a table? No, it's not an integer. So that's what I mean by operations. So what operations can I do on one table? Suppose you have a number, you have another number, a so-called binary operation that involves two different objects of the type. Can be like multiplication because I can multiply two numbers. I can divide two numbers. I can do one number raised to another number, right? I can subtract numbers, I can find the geometric mean by multiplying numbers and taking square roots. All of those are called operations. So now we ask a very important question. When you have a table full of data like this, what operations can you do on one table? And then also what operations can you do on two tables? And then by extension, more than two. So it's very interesting to think of tables as data, okay? Data types. That is exactly Card's genius, Ed Card's genius. Yeah, you can do add and subtract, correct? You can do a lot actually. So I'm going to tell you, okay, that's what's coming next. That's a slightly different object idea, okay? So it's not about creating, updating. That's not what we're talking about. So not that. You can do union, correct? Yeah, okay. So if you actually wait, then I can tell you things. You can type, by the way. I'm not telling you not to type, but sometimes be careful because what happens is if you type something that is incorrect, a lot of people would read that. And then they would be like thrown off, okay? So it's not CRUD. I mean, CRUD is a different idea. This one just simply says before you get to any of that, conceptually, what can you do with two tables, okay? You can add, subtract. You can actually multiply them. You can divide them. Wow. Okay, so those operations are called algebra. That's all. So relational algebra literally means what operations can I do on one table, two tables? Yes, you can do union. You can also do intersection. Yes, and difference. Okay, so such operations, which we're going to name pretty soon, all of those, they're called relational operators. Very simple. If I ever put a table in a variable name, then the variable name would be called a rel var. So just forget this part, okay? But mostly it is this. Okay, so the magic that Card had was this. Card names 8 operations that you can do. Some you can do just on one table. Some you need two tables. But here's the magic. If one of those operations, I'm going to call it like some operation, involves, for example, only one table, okay? It's like this. I send the table into an operation like a function call, a call operation with a table. The magic is he made sure that the result is also a table. One such operation is simply you give it a table and you say, I don't need that last column. Go to every student and just delete the advisor. I need to know the advisor's name. Give me a new table where the advisor name column is gone. Such an operation is actually one that Card named. A different operation will actually operate on rows. I can give it a whole table of all the students and tell the operation, give me only the students that have GPA more than 3.9. Okay, I'll get the top students here, right? This will have fewer number of rows compared to this one. These are all the students. It's a short list that only have 3.9 or higher. That is called the selection operation. That's probably one of the most important of the 8 that Card named. That's the row operation. So there's some that only need one table, okay, to operate. But the magic is you'll always get a table as a result back. Many other operations need two tables. Okay, so they're called binary operations. So this binary operation would need a table here and also a table here, such as union between them. But the magic is the result will also be another table. The same data in, same data type out. Okay, then you can do something pretty surprisingly cool. You can start to combine and connect all these operations. That is called chaining, and then that is possible because of this cool idea called closure. Okay, supposing I have a table here that has all these columns. I don't need these columns. I don't need these columns. Then I give it to what is called the project operator. The project operator is the one that deletes columns. So I give it the table and I give it the column names and say delete those column names. I'm going to get all the rows back. I'm going to get all the rows back that I had, but then not those 2 columns, all the other columns. So I get all the rows back. Now I can take a different table, which is very similar. These columns are all very similar, but these columns again are different. Those are different. So I take the project operator one more time and I say take this table and delete those and give me a new result back. So now something cool happens when I get this back. These columns and these columns are 100% identical, Wow, I can maybe put the two tables below each other and make a new long table. That is called the union operation. I'm going to make a union operation and tell the union blindly just combine them, meaning put the rows below each other and give me a new long table back. So I'm going to get a long table back that has all the rows. Either B can go first or A can go first, meaning it doesn't matter which is on top of what, right? Order doesn't matter. It's called the union operation. Then I can take that and do a selection operation on it. In this master list, give me all the people that are graduating this year. People that are graduating this year. Then I can pass that to a selection operation and say of the people that are graduating this year who are all in Viterbi, selection operation. Then I get that. The point is I can go on chaining them. By chaining, I mean all the operations are joined together like a hierarchy, okay? Like a tree. I can make a whole tree of operations where the leaf nodes are all these tables. So a tree is like a real tree. So I start with all the leaf operators and then leaf tables rather, and I do operations and get new tables, do operation, get new table, and then put them in some other operation. So I might end up with one cool little table at the very end, like a real tree. So that's the operation chain, operator chain. It's a hierarchy. That is possible because of a very important idea where same type in, same type out. When that happens, such an operation is supposed to provide what is called closure. Closure means a group of operations that can all be joined in any order and nothing bad will happen. For example, I can take two numbers and divide them, and then I can raise them to something else, and then I can add them to something, and then I can divide that by something else, and then I can subtract that from something, and then raise that to something. Because division, subtraction, addition, exponentiation are all a group of operations that provide what is called closure. I cannot do square root, by the way. Square root is not part of the closure because if something here, say I subtracted 1,000,000, if this becomes negative and I take the square root, all of a sudden I'm not getting numbers, standard numbers anymore. I'm not getting standard real numbers. I'll start to get complex numbers. So in the world of real numbers, there's no closure that includes a square root operator. If I want a closure that also includes square root, then that operates on the list of complex numbers. So if complex numbers are okay with you, then square root says, hey, I'm also part of the closure because any operation that we provide will all result in complex numbers or not. All right, so the closure idea is a very cool idea. All you need to know is in relational algebra, every one of those operations is providing closure. Table in, table out, tables in, tables out. Now I think you're ready to see what those operations are. Okay, so I can ask you this in the after the break, little discussion, because other things also have closure, and I want to ask you what operations, come with that closure. Operations lead to closure. All right, so this is what I just told you, so we can skip it. So tables in, table out, the 8 operators, all of them. I gave you the paper in extras, okay? If all this fascinates you afterwards, go reread this paper. The extras that I put up, that paper defines all the 8 that I'm going to tell you. In 1970, wow, it was really forward thinking. Yeah, so then here they all are. I'm verbally going to tell you, you guys named it there, and then we'll do examples for each one of them. A select operation is row filtering. What if you could examine every single row for some if statement and only give you some rows that pass the if statement? It's like for every row, if GPA more than 3.9 and department equal to computer science and graduation is spring 21, output the student. I want to congratulate them because they're graduating pretty soon and they have a high GPA. I want to send them a card. So that calculation, if this and this and this for every row, and only rows that pass would come out. You do that in SQL. It's literally select, first name, last name from student table where GPA more than 3.9 and department equal to CS and graduation date equals 21. Then write like a little SQL statement and run this on like 40,000 students and it'll just pop it out instant. Therefore, that is the row calculation operation. This is the column operation. So project means only give me the columns that I need, throw all the other columns out. Okay, project means keep. So of all the columns, I'll name a subset of the columns, and then you will output just a subset. All the rows, don't do any if statements on the rows. So together, they're very useful to do things. Union is what I showed you here. If columns are all identical, then you can combine them and make a new table with all the columns in it. Intersection means when you have more than one column, when you have more than one row, what are the, what are the things in both the tables where if there was a row here, the row is also here. So then that's a set intersection. If this table was set A, this table was set B. Union is all of them, just combine them, that is union. Intersection is over here. It says what is common to this table and to this table. That's the intersection operation. A difference is what is all only in the first table, but not in the second table, A minus B. If some row was here and here, don't name it. Give me only things that are unique to A, okay? That's called A minus B. Conversely, you could do the opposite. Give me only something that is in B, but not in A. So that's called B minus A. That is the intersection. Sorry, that's the difference operation again. There are two differences, A minus B, B minus A. They're not the same. But A union B and B union A are the same. A intersection B, B intersection A are the same. What is that called when the order doesn't matter? What is such an operation called? What is this operation called? When it doesn't matter whether you say A union B or B union A, order doesn't matter. Such an operation is called commutation. Yeah, correct. Commutation is when order doesn't matter. When order matters, it's not commutation. Here, order matters, okay? So then division is not a commutative operator. Okay, so union and intersection are definitely commutative, but the difference is not because you will get two different answers. Imagine that this is the list of all the students who go to Viterbi. This is all the students who go to Keck. And for Viterbi students, you hold extra information about undergraduate GPAs. For Keck, you hold information about their birthdays. We cannot do union or intersection because some columns are not identical. So you start by doing a project on both of them. So project the Viterbi students and say throw away the undergrad GPA. Project the Keck students and say throw away their birth date. So then the columns that remain are all just academic columns. Then I can say, give me A minus B. Who are the students who are only in Viterbi who are not taking medical classes, like they're not BME? Then you will get only Viterbi engineering students. Conversely, who are the medical students not taking any Viterbi classes? The intersection is fascinating. Who are the people taking classes on both campuses? Maybe they're BME or pre-med or something, right? Or some computer science business, for hospital administration. So then that'll be the intersection. It's cool, right? So you can do all this in real world. Union, intersection, difference. Product is weird. Product would actually multiply all the columns here by all the columns here. So you'll have this new fake table that looks like so weird. It's not going to be, it won't have entity integrity. It'll have so many failures. So for every column value here, you would actually multiply by all the values here. I'll give you better examples pretty soon. So what will end up happening is you will get a pretty weird table that has all these columns and these columns. Columns in A, columns in B. The number of rows would be number of rows here multiplied by the number of rows here. Because for every value, you would use every other value. So you'll get this crazy looking table that is called the multiplication. It's called the product. And we use it for temporary calculations. That's not a real table. You shouldn't save it to disk because it's a bad table. Join is easy. So join is the table column names don't even have to be the same. At least one of them has to be the same. Again, say you have student here. Then say you have sports here. Sports, where the student is a foreign key. Say you have library books, all the things the students borrow. Every time you borrow a book, 1, 2, 3, 4. And here's a student who borrowed the book. Here's the restaurants on campus. Every time students go and eat, the restaurants make an entry, and then here's a student. Now, all of a sudden, I'm quite fascinated by student number 45. Tell me the student's entire history. Give me the academic information, give me the sports information, and also give me the library books that they read, and tell me what food they eat. As long as this 45 is also here, how many other times? And also here, and also here. I can join all of them together, right? That's exactly what the magical join operation is. The join operation doesn't care about what these columns are, as long as there are some common columns between any number of tables. Join is so powerful that at runtime, it's not compile time, meaning we don't have another table that has all these together. We don't want that. It's a bad idea. So keep them separate, but write a SQL query that knows to go and look through all of these tables and do multiple if statements. And then when things join, then you will literally get this long row. This table will have just the student. This right, you'll get a long table because you joined them. And then you'll have many results. The student ate many times, borrowed many books. So then you'll have 1, 2, 3, 4. If there was a student ID column, it'll be the same 45, so we probably don't need that. But this is where all the useful information is. What books and what, food they ate, what, sports they played. It's all about that one student. You can find out by joining tables together. So join is like one of the most powerful operations. Join and select are probably why SQL actually exists, okay? So join and select are like radically powerful. Others are more like helpers, to make them happen. Divide is so weird. I have examples for each one of these, so you can bear with me. But right now, just to tell you, you can divide one table by another table, which is so strange. What does it even mean, okay? And then surprisingly, of all those 8 1, 2, 3, 4, 5, 6, 7, 8. Divide is the only one that has no SQL command. So divide does not have a SQL command. It's so weird that the SQL committee left divide out. But thankfully, we can implement our own divide using the other 7. So divide is interesting. And divide has a use, by the way, okay? You can definitely use divide in calculations, but it never became an actual SQL command. Interestingly, you can implement divide yourself using the other 7 operators in more than one way. There are probably 4 or even 5 different solutions that all divide this table by this table and get that result. But you can do it in so many different ways, okay? It's interesting to even come up with all of them. In the SQL homework, sometimes I make that extra credit. It's a division question, and I say if you do it right in other ways, the second way and the third way, you get extra points. Okay. So therefore, these operators that Card had in the paper, they basically became SQL. And now I want to show you examples for every one of the 8, okay? Okay, so first some words and then some, this is how it looks like. There's some text and then I have like an example, and then some text and then some example. So I'll cover them all, okay? They're pretty simple. They're all simple. They're fun. Like, wow, Card, you're smart. Just thought of it. Select is called restrict because you're restricting the result to a few rows, not all the rows. So it means I give you a table and then I ask you a question like an if statement, a selection condition, and then you will make sure that you obey the condition and give me potentially a small list of rows. Supposing you have so many rows. The select operator, on the one hand, depending on what you ask, can give you the whole table back. Suppose you say to select, give me all the students whose GPA is more than 0, greater than or equal to 0. That's hopefully a silly, query because everybody has GPA more than 0. You'll get your entire table back. That is one extreme. The other extreme is at US GPAs don't go more than like 4 or 5. So give me all the students whose GPA is more than 9.5. Okay, then you'll get an empty table. You'll get a table with nothing because no row qualifies. So those are the 2 extremes, okay? You get a null set versus everything, and in between is in between. So that is the selection. It's a horizontal subset, meaning filtered rows, only rows that pass the test. Projection is a column operation. It eats a vertical subset. That means, again, suppose it's now projection. If I have all these columns, on the one hand, I can tell the project operation, just give me all the columns back. I just want to check what it looks like. Okay, you'll get all of them back. On the other hand, you can say to project, give me no column back, which is weird. And you'll get the empty table again. In reality, you will throw away the columns you don't need, okay, 1 or 2 of them, and you'll get a smaller table vertically, meaning chop off like extras. Union is if the column names are identical, and that is called union compatible, meaning if I have 2 tables, I want to do a union, I have another table here. It is all the same as before, like salesperson, this one car dealership, all the salespeople in car dealership, they have a salesperson ID, they have the salary, manager's name, how many cars they sold last year, what is the spouse's name, what is the birthday, what. This one has very similar information, a different car dealership, all the salespeople are here. But here they also store something else, like what other car dealership did you work before coming here? How many years did you work? Just because of that extra, it is not here. You cannot simply do a union between them because that information is going to be missing. So the union operation would fail. It says the columns are not compatible. So the first thing you have to do as a pre-operation is you got to get rid of this using a projection. After that, you can do a union. So you take the second table, send it through a projection operation. And the first table doesn't need to go through a projection operation. Then you can do a union. You will get the long result. So this is like a pre-filtering, data filtering operation, but it's possible because, again, closure, okay? All right, so that is what a union compatible means. It means the column name should be the same. They don't have to be in the same order, by the way. If this is salesperson's name, the name can be over here. Conceptually, logically, they should all match, that's all. Okay. Unary means single. Union, the result of union means single table. Yeah, unioning means putting them together. Again, all the Viterbi students, everybody is a Viterbi student. All the Keck students, all of them, and Viterbi. So anybody that lands here, they're in Viterbi and in Keck, right? So that is what union means. Union means give me everybody. And those people in the middle, count them only once. Obviously, there are no 2 students, right? The same ID. So union will automatically keep only one instance of, the rows if they occur twice. In other words, supposing this is again Viterbi, this is Keck. The student who's taking all these Viterbi courses obviously has a student ID and all the information. The same student is in the Keck database also, same student ID, same everything. We cannot blindly just union them, because then the table is bad because the student is there twice. So the system knows to not do that. System will automatically only join correctly, will union correctly. Okay, that's all a union was. Intersect is easy, yields only the rows that appear in both tables. So intersection can be null. Supposing in a school, there's nobody in Viterbi going to Keck, no one in Keck going to Viterbi. If you say who's in the middle, who's in both schools? Well, nobody. So null is okay. In all of these, a null table is an okay result. A null table is literally a table with 0 rows and 0 columns. But mathematically, it's still a table. Okay, meaning you can send it to closure. Okay, so union forms a copy. Yeah, all of these are copies. Okay, so you don't destroy the originals ever. You always get copies, because you can save the copy as a new table if you want, and then not do this operation over and over again. You will never destroy the original. Okay, all these operators make copies. Yeah, so there's no pointers you send to all these tables. You will always get a copy. For union, do the columns need to be exactly this? Yes, absolutely, 100%. For union, the column names, types, they have to match. Mostly types. Names you can alias them. Alias means temporarily you can rename them, but the types have to match. And one cannot have more columns than the other, because in the other you don't know what to do. It's all about data integrity. Okay, you don't want nulls. Common sense, right? But yes, they have to match. Which is why you can get rid of the things that don't match. Why does the second table go through? Yeah, exactly. It has more columns. So sometimes I go a little fast and I tell you things that you might miss. So what I said about the car dealership was this: in one car dealership, imagine car dealerships merge. Okay, so BMW of Glendale, BMW of Santa Monica. So they want to go in like a Beverly Hills in the middle. They want to have a Beverly Hills BMW. Hire all these salespeople. So I want to merge my tables together. Except Glendale BMW has some extra information like date of birth of the salespeople. Santa Monica BMW has like a spouse's name. So you cannot simply union both of them and make a new table here that is union about them, because this column is not here, this column is not here. Therefore, you have to do a project operation and tell this project, give me all these columns but not the date of birth. So then I'll get everything except the date of birth. It's snipping. With scissors, cut, throw it away. In here, you tell a different project operation, throw away the spouse's name, we don't need that anymore. So then I'll get a new table without the spouse's name. And now it is 100% column, the union compatible. Then I can union them. That's what I did previously. Why not the second table? Yeah, right. Yeah, sorry, I answered that again. You can do project on neither. If they're already okay, no project. Or you project both of them if each one has incompatible columns with the other. Or you project none because already they're okay. These are all just simply, a function of like what tables you start with. Any other questions? Okay, so let's move on. I'm going to start giving you examples now. Select is like probably the most super powerful, because all of SQL queries ultimately select something. Okay, so it's select. Let me make it a little bit bigger. Select all. First of all, these are real SQL commands, by the way, so you can type them in pretty soon. Well, select star, exactly. So select star means no filtering. Give me every row, every column, like a sanity check. I just want to make sure my table looks right. So then select star, select all. You will get the whole table back, okay? No filtering. On the other hand, select only price less than 2. So you will actually say, where price less than. So go here in my little store and pick out only things that are cheaper than $2. 9-volt battery, 100 watts bulb, right? That's what you get. So that is the result of that query, like an if statement. For each row, if price is less than 2, output the product code, product description, and the price. I want to look at how cheap it is really. Or this is a different operation. Go back in the table. Give me only that product code, So somebody's complaining about that product, so I want to know what the product actually says. Like in the receipt, it says this. I don't know what it's actually called. Oh, power drill. So you go and search, you literally do a match, because you'll only get one row by definition. Product code is unique. So look for 311452. Look for one student. When your advisor types your student ID in, this is exactly what they do. Just pull up the student's information. Easy, right? So select is trivial. But gradually we make these conditions more and more complicated. That's why SQL is cool. But conceptually, it's a really, really easy idea. So project. Again, project followed by a column, comma, many column names. You'll only get the column or the column names. Again, go back to my table that I had before. I only want to know the price. Don't tell me about the products. I just want to stare at all the different prices we have in our store. Okay, I'll only show you the price column, and I can sort them afterwards. Or give me the product description and the price. I don't care about IDs. Who remembers IDs? Just tell me the name. This is usually what we search in catalogs. Okay, in Amazon catalog, this is what shows up. You're projecting, leaving out the ID. The ID is just for internal managers. You don't need to know the ID. On the other hand, you can do this. You can say, give me the ID and the price. You can do any combination of those. It's called project. Really easy, right? So far, so good. Easy. In the Unix command line, I can take two different files. I can touch two files. I can say cat AB. I'll get a new file, right? That's what the cat command is. Cat concatenates. So cat A, let's say 1, 2, 3, 4. Okay, and then we can do a cat B, right? We can make a B file, like 6, 7, 8, like that, and then you can cat them together. So what if you say cat AB? So it got together, right? Then I can write that to a new file. I can say cat AB, redirect that to some new file called CCC. And then now I can see what that looks like, and now I have CCC. So now I combine data. That's exactly what the union does. So union takes like one table, another table, literally puts them together, gives me a new table. Cat command, like this. So again, say these are hardware stores. This is your hardware store, my hardware store. We decide to merge and become one hardware store. As long as our columns are mergeable, both have a P code, both have a description, both have a price. I can now have a new one where I cut one and put below each other. I can put A below B, B below A, doesn't matter. I have a bigger store that has more products now. That's all the union operation is. Union is very simple, right? Intersection. We're merging stores. Is there anything we're both selling? What about the duplicates? Yeah, so duplicates are included only once. I think I told you that earlier, so because in the student example, suppose a student signs up to classes in both campuses and you try to find the list of, students who go to both schools. You cannot have the student twice. So naturally, the system will actually use the duplicate only one time. But there's a flag in SQL. It's called union all. You can say union all, and temporarily, just so I can see who such students are, give me an illegal table that has 100% duplicates. That's called union all. So you can see like what the duplicates are. And then for the real calculation, go back to saying union, okay? So if you want, you can look at the duplicates. But by default, it leaves out duplicates. Okay, so intersection. Say these are employees from two different companies, and then you want to like merge them or something. Like who worked, say this is company A, company B, who worked in both companies? Okay, so Franklin Johnson, as you can see. Except in reality, this could be billion rows, that could be billion rows, and you'll still get the result. It's really pretty cool. Okay. Hospitals, who stayed in this hospital and that hospital. You can actually find out who went to this pharmacy and who went to the pharmacy, bought the same drug. You can catch people by like doing all this. Intersection. By the way, when you can intersect 2, right, by definition, you can intersect 10. Like I can add 5 numbers together, but in reality, I'm adding 2 at a time. So binary operators can be, be more than 2. Just do them one at a time. Union is the same thing. I can union 10 tables together. It really does it 2 at a time. You take the first 2, union with the third one, take the result, union, union. I have a tree of unions, really. Okay, so like a tree of intersections is also possible. Difference. Difference is when you say what is in set A but not in set B. Again, it makes sense to think of them as just set operations. Pick a different color. Supposing again, this one set, this second set. Then we ask, union means all of them. Intersection means who's here. If this set was called A and this set was called B, A difference B, the order matters, so they're not commutation. A minus B means just this little part. Who is in A, but then who is not in B? So only this part is A minus B. Conversely, this part would be B minus A because they're only in B, but they're not in A. Nice, right? Okay. That's what difference was. And again, for difference to work, same thing, the column names should be identical. For union, difference, and intersection, that holds. It should make sense for these operations to happen. So you cannot randomly subtract weird tables that have different columns. So you have to project and make sure that columns are all compatible. Then you can do all the 3 set operations, union, intersection, and difference. Product is the weird one. So product is when all possible pairs of rows. So take the rows in A, take the rows in B. And the tables, by the way, don't have to be the same students or anything. I can multiply a student table by a restaurant table. It's like highly bizarre, okay? Just multiply anything by anything. Then I'll get a new table that has the number of rows to be the product of the two row counts. The number of columns is the sum of the two column counts. So you have in your table 5 columns. I have in my table 8 columns. The product will have 13 columns. So I'm going to show you right now. You would use it as a temporary, you know, like a literally a temporary operation, and then you will filter something from there and make a real operation happen. Specifically for joining, one way to understand join is actually do a product and then do a select within that product. That is exactly what I'm actually going to show you, okay? So when we get to join, I'll actually show you the join example. We'll actually do a product like that and then do a select, but not yet. Okay, so then we finish difference, differences. In fact, that's what we're looking at. Differences again, who is in one but not the other. So when we say A, difference B, it means people only in A. Franklin is the only one common, right? So in here, there should not be Franklin. If we take Franklin out, others are all unique to A. What about B minus A? So who will be in B minus A? Can you tell me? Who's going to be in this minus this? Who are the people only in table B but not table A? You can just name their, first name. Sure. William. Who else? Yeah. Correct. William Franklin. In fact, the same one that was the intersection, right? They're the ones that are to be left out. In other words, there's something very cool going on, which is when you put all the three together, this is A minus B, right? And then this is A intersection B. And this happens to be B minus A. If you union all of them, right? That's what A union B is, right? What we call A union B is really A minus B on the one hand. A minus B on the one hand. This is A minus B. And then A intersection B. And then B intersection A. That is actually what A union B is, okay? So that's what we're doing here. In other words, previously you told me that Franklin is in both places. Then when I ask you what is A minus B, then you should leave Franklin out. So anybody that is in both, if you leave them out from this table, you will get A minus B. If anything that is in both tables, you leave them out from this table, you will get B minus A. Okay, so you guys are all correct. So in difference, column attributes are not necessarily this. No, they have to be. They have to be. In difference, union, and intersection, the column attributes must be identical. Otherwise, you cannot do a difference, okay? Isn't Franklin Lopez also in B minus A? Franklin Lopez must not, well, wait. Yeah, sure. Franklin Johnson is not the one that is in B minus A. So I'll give you the answer, okay? In B minus A, Franklin Lopez, William, and Susan Rogers are in B minus A. In A minus B, George, Jane, Peter, and Martin are in A minus B. In other words, only the person that is common to both of them is not in A minus B or B minus A. All right? Okay, cool. Again, it's the little diagram that I drew, okay? So B minus A contains 3 rows, exactly. B minus A contains, again, just for the record, Franklin Lopez, William Turner, Susan Rogers. Pretty soon, you guys can do this yourself. You can actually get a small little SQL, program. You can even do it online, and then type this table, and then type SQL. And you'll find out. In implementation, yeah, it absolutely is. Unfortunately, there's no way around it. Okay, yes, you have to compare practically every row with every other row. Yeah, correct. Use don't once it doesn't. Yeah, correct. Good, and good. Product. What the heck is a product? First of all, what does it look like? Product looks like this. 3 columns, just by coincidence. And the columns have nothing, 0 to do with each other. But I put the columns next to each other. So in product, that's what will happen. 6 rows, 3 rows. 6 times 3 is 18. You will see 18 rows here. Because I will take literally the first row here, right? 1, 2, 3, 4, 5, 6, flashlight 5.26. Flashlight 5.26. Because there are 3 here, I make 3 of those. And I stick 1, 2, 3. In other words, I'm multiplying the first row by all of this. That is why I'm getting my first 3 rows of data. I'm taking my whole second row, multiplying by the entire table. That is why I'm getting my lamp. I'm taking my box fan, multiplying by 3 rows, box fan, box fan, box fan. 9-volt battery 3 times, 100-watt bulb 3 times, power drill 3 times. You understand? That is what the product is. Do columns need to be? They don't need to be. They could be identical. It doesn't care is what the answer is. It doesn't look for it, okay? There's no condition either way. It just blindly puts them together. But there's no primary key column here, right? So if I asked you, what could be the primary key here? There's no individual, no composite. There's something that is, the same in 2 rows, right? So in that sense, well, I guess you could make that combination. You could make the whole, one of them to be like a primary. You think about it, even that is not possible, okay? So the question is, what could be like good primary keys? The idea is that you would never use this for any like storage purposes. It's not a real table. But you can go through this table and look for things and then filter like a smaller table out. Yeah, the application of the multiplication operation is to make your own join. You can write your own join and put some fancy conditions in that join, because there are join conditions that come with SQL. Join commands come with SQL because join is one of the most common things. But you want to do crazy joins. You want to join some row here with some other row here, not if they're identical, if they're 10% more, okay? So say there's some column here, some other column here. You don't want equality. Equality would be primary key, foreign key. But then you say, the columns are numerical. There's $10 and there's like a bunch of dollars. Look for all the numbers and join this column with, meaning join this whole row with some other row. Not if 10 equal to 10, but say this can be 10.05. I don't mind a 5% change. I can make any weird rule that I want in SQL. And this product is the first step in doing that. Okay? Yeah, sure. Yes, correct. So, Garima thought about it and said, wow, what the hell can be the primary key here? It's basically, the store ID product code. Okay? See if that is true. Okay, see the store ID product code, right? That definitely does not repeat. That's pretty smart. But it still has so much redundant information. Okay, look at all this repetition. We don't want anywhere, as much as possible, too much things repeating. So we throw it away. We're going to use this as a temporary operation to do joins. So let me do that, okay? All right, so there's many kinds of joins, first of all. In fact, the join that I named, I just verbally told you about a join that is weird. Joins usually mean the same student here should be the same student here. Then this entire row can be joined with this entire row. That is actually what joins mean. Yeah, those are a little bit different. On the other hand, that's called equality join. When you join something, you join based on equality. Like this ID is the same as that ID. So I'm going to assume, unless you're weird, that the student is that student. So I hope on purpose it's not some other university where the same ID means 100% different student. We don't think that. We assume that this ID is that ID. Then when you join things based on equality, that is called equal join. It's called equijoin. Equijoin. It's actually called equijoin. But we can have other joins called theta joins. Equijoin is joining based on equality conditions. When some cell here is also equal to a cell here, I can pretend that all the row of information about that individual can be joined with all this information, which is also about this individual. I can put them together and make like one long thing. That is usually what we assume. But like I just told you, you can do the other way it joins, where you can say there's a table here with some column value, a very different table here with similar column value, like a price value. But don't look for price equal to 25, price equal to 25. We look for price equal to 25 matching price not equal to 25. So join any row where this is not 25. So I can do a not equal to join. Not equal to join. I can do a less than join. Join two rows where if this is less than that, join any such row. I can do a greater than join. Less than or equal to, greater than or equal to. All these joins are called theta joins. This is called equijoin. So it's a complement of that. Therefore, you can manually do all of these. You can do not just strictly greater than, but you can say less than. You can say if it is less than, like if it's off by 10%. So 90% the same, the subtracts the difference between them, absolute difference between them should be less than 10%. So you could write your own weird join rules like that. But the starting point again is like that. Okay, so products. Therefore, again, join is many kinds of joins intelligently, all based on these values being the same or being different. And then this is about the divide operation, the strange divide that I told you. To divide, you cannot divide any table by any table. The top part. So in a division, what is the top part called? What is the bottom part called? Dividend divisor. So what is the top part called? What is the bottom part called? What do you call the top when you divide something? Dividend. What about the bottom? Divisor. You can call it numerator, denominator if you want, okay? But yeah, similar things. This technically called the divisor, dividend divisor. Yeah. Okay, so dividend, the top part, has to always be 2 columns. Wow, cool. And the bottom part always must be a single column table. If you have more here, you have to project and throw them away. If you have more here, project and throw them away. So division is a very strange operation that always divides a 2 column table by a 1 column table. Why? I'll tell you. If you wait, I'll tell you. Okay, so time for examples. Told you. We read a little bit and then we look at examples. A natural join is you tell SQL, pretty soon you can tell Alexa, by the way, you can talk to Alexa and say, Alexa, join students and restaurants. Done. What do you want to call it? It'll be that simple. It already actually is that simple. If that is possible, it's possible because of something called natural join. It's called natural because somehow the column names are so nicely named so that a column name from one table was the same as a column name in another table. So all you need as an input for joining is just the table names, okay, no column names at all. Such columns are called natural joins. If a column here was called student ID, and then some other column here was also called student ID, to join them, to see, if any student here, how many times did it occur here, and then put this information together with all of that information. Joining. I don't need to say anything other than the table's name. Join table A, natural join table A, comma, table B. That's all I have to say. Because the system will check every column name against every other column name. Again, it's an n squared operation. And as long as it finds a column that is common, it will use the fact that this row has an identical value here to join. Or if there's nothing matching anywhere, the join would be empty. Suppose there are 2 column names that match. Suppose it's GPA, okay, and also GPA. Then if you say natural join, then the value here and value here must match a value here and value here. Okay. Then natural join, that's what it does. So it looks for common column name or common column names. It only wants from you table name. On the other hand, suppose I call this stu ID, the natural join would not work. Because magically, God doesn't tell the system that SID means the same as student ID. You know that, I know that, okay, but SQL doesn't know that. So then you wouldn't do natural join. You can still join it, but now you'd have a join condition. Now you'd have to say SID.GPA, equal to student ID, something like that, right? Or sorry, table A.SID equal to table B.student ID, okay? So you have to name the columns yourself, and then things will work. But otherwise, natural join is pretty simple. All right, so let's move on, okay? Those columns that are used for joining, it doesn't matter what they're called. If you join based on certain columns, they're called join columns. So join columns are the ones that do all the magic, like primary key, foreign key. Except when you join, you can join 2 tables where the columns are not primary keys at all, okay? You can still join. So there was a table here, primary key, and there's some column here called C, column C. In some other table, entirely altogether different table. A different primary key, but also a C column. In neither table is C a primary key or a foreign key. The concept doesn't even exist, but I can still join these tables based on the fact that some value here is also here and also here. Then I would combine this row, that row, okay? So joining is a very flexible operation. Don't get confused by primary keys, foreign keys. It's all about join columns. Okay, so equi-join is the most intuitive kind of join where we think that any value must match any other value. This has a city named Los Angeles. This also says Los Angeles. Okay, then I'm going to combine both of them because we're talking about the same city. Equi-join, equality, strict equality. Any other thing that is not equality, the 5 other operators that we named. In programming, when you have 2 variables A, B, right? You can do strict equality comparison. Tell me if A equal to B. Tell me if A is not equal to B. Tell me if A is less than B. If A and B are equal, this condition would fail. Tell me if A is less than or equal to B. If they're both equal, no, you'll succeed. Tell me strictly greater than, greater than or equal to, strictly great, great or equal. So not equal, less than or equal, great, greater than or equal. All of these 5, they're like the non-equality. They're all called theta joins. So you call them an extension of natural join. But what is so cool is, they let you do very cool operations. I told you can do some very fancy calculations where you can join tables based on the fact that this salary is less than this salary, or the stock price is less than the stock price. You can do like some neat comparisons. We are not restricted by the truth anymore. It's not things have to be equal. Things can be less, things can be more, or completely not equal. Like, make a list of all my enemies, okay? And then I'm gonna go kill them. If I have a list of friends and non-enemies, I mark everybody into a friend or enemy. If I want to invite people for my birthday party, then I would want to pick my friends. But now I can invite that list and say, give me my enemies. Just making funny remarks, but it's true though. That's what equijoin is. It's the complement of, get a join. It's everything that is not equal. The inner order that one of the students named, that's a different idea. So let's actually illustrate that. This goes back to saying, what if column names are not completely, unique? What are you going to do? It's all about, left, right. Okay, so when we have two different tables like this, tables, you're trying to do some join operation. If the join operation returns rows that are based on the joins, so say some value, match some value matched here, right? And then only based on those rows matching, you'll get a new row. Anytime there's a match between table A and table B, you're going to get a row, okay? You're going to get a row. That is what you think of joining means. I go through every single value in the join column, see if there's some match, and every time there's a match, I make a new row for you. When that happens, that is called inner join. Only returns matched records from the tables that are being joined. That is what we expect, okay? The output of join is a new table. Its output of join always is a new table, and the table can have any column you want. You name the columns, okay? Yeah, so I'm going to show you the example. Actually, it's right here. I'm going to do it right there. We'll actually find out customers and who's selling cars, okay? You can wait for that. But I'll tell you about the whole outer inner business. When you join, and then the result is based just only on the values matching, that is called inner join. And that is what you normally expect. But then for some reason, sometimes you think, I want to know my output should consist of every row in column, in table A. Let's call them table A, table B. Let's call this a left table. Let's call this a right table. Even if no join happens in my result, I still want to see every single row in my left table because I like my left table very much. So if there are 10 rows here, I expect to see all 10 rows here. Even if those 10 rows all don't match here, but I want to see all the 10 rows, okay? That is called a left outer join. Yields all of the rows in the first table, including those that do not have a matching value in the second table. For some row, that value didn't match anybody. I'll still give you the value so you can look at it. That is called a left outer join. Conversely, right outer join says, I want to look at all my right table rows. So even if there's no match for some of these rows, my result should contain exactly how many of our rows are here. That is the right outer join. Full outer join is left outer join and right outer join. Okay, so it means I want to see all the rows that are here and also all the rows that are here. The crazy thing is, if you do that, because some of the rows are not matching, some of those in here, you're going to get some nulls, okay? You're going to get some null values. And because some here don't match here as well, right? You get some null values. So this outer join is very interesting in terms of, left, right, full. So I'll show you an example that'll make it very clear for you. But then if you leave the whole outer, so outer means can be left, can be right, can be full. All those are called outer, okay? There's no full here, but full would just mean, left union right, still called outer. On the other hand, inner is you will not see anything extra. Wouldn't left, right, or join return table? No, I mean, there could be joins, right? So when you do a full outer join, which is left, right, outer join, it's going to show you new rows that are actually joined rows. So you'll not just automatically get some kind of A union B, okay? But the example that I show you, it'll make it clear for you. It'll still show you what is joined, but also show you rows that have no joins. It'll leave the other side blank. You're going to see some nulls when you do, left, outer, right. Again, nothing like an example. Example, select, seal, and clarify everything. So we will do that. So in fact, we'll do them now. First of all, we'll do the join operation manually by multiplying. All right, so now comes a very interesting problem, meaning a sales manager says to themselves, we've been selling cars like all year. We want to find and reward the best employees. Conversely, we also want to find the dead weights that didn't sell any cars. Get rid of them, fire them, replace them with better employees. So then what would you do, right? You have a customer table where every customer has an ID, like an Amazon account number. They have the names and they have the zip code. But most importantly, who is the salesperson who sold the customer a car? Every time a new customer comes and buys a car from some salesperson, the car saleswoman's ID shows up here. Even here you can tell 231 is a good salesperson, sold 2 cars. 125 is equally good, sold 2 cars again. 167, 420, not bad, something better. But what about 333? Hey, wait, I don't see them here at all. That person never sold any cars. That is the kind of thing you can expose by doing left outer join, right outer join, or full outer join. Okay, we're going to do joins now, which is by multiplying and then finding who sold, what car to whom, okay? Meaning you want a new result where all you want is after 231, you want their phone number. After 167, you want the phone number. So you're trying to join the two tables together, but then how will you do it manually? How will you do a product? And then how will you eliminate duplicate information? Okay, so again, natural join based on column names, okay? That's pretty simple. How can you make a natural join yourself? Just based on the table names alone, you would multiply, and then you do a select, filter some rows out, duplicate rows out, filter some duplicate columns out. Let's project, and you will get the result that you want. So let's do it, okay? First step is just blind multiply. What will happen if you multiply every single customer with every salesman, even though the customer was not serviced by that salesperson at all? Then you get duplicate fake information, but then you'll throw it out, like here. So what if you did this? For Walker, who really was serviced by, like say this agent, right? Sorry, this agent, 231. You blindly paste all the agents that work there. So therefore, 231 is matched by an actual 231 here. This is the real row you eventually want, okay? You don't want this row, this fake information. Fake news, but you still do it anyway. Likewise, Adoris was sold a car by 125. So only 125 should match, because you see what you did when you multiplied. You simply put the customer information and the salesperson information together. So now you see why you have to project, because the column name is in there twice, the ID. Also, when you multiply, you cannot have two columns, both called agent code. Okay, think about it. Because agent code was a primary key and a foreign key previously. But now you want to put them next to each other, so we have a new little problem. So how do we solve the problem? We use a table name dot column name, table name dot same column name. This is called name spacing, like you do in programming. So then the problem goes away. Oops. Yeah. So what I meant to show you was this agent code was not a problem previously. Oh, that's just the image. So sorry. Here, before you do the multiplication, it's not a problem, right? Because you see the agent code was a separate table only one time. This table had a primary key agent code. But now I insist on putting these two columns next to each other and multiplying all the rows. So I have agent code and agent code. So that's not a valid table anymore when I have two different columns, not the same column name, right? Because column names have to be unique, obviously. So we call this temporarily customer.agent code. We call this temporarily agent.agent code. That's all I'm going to show you. Okay. So therefore, so far, that's all we've done. We've just simply taken every single customer, and because there are four salespeople doing things, we just simply repeat them in like 4 times for every salesperson. Now you want to do a filter. And what will the filter look like? The filter would just say, give me only all the rows where this column matches this column. Okay, this is a selection operation. Let's do a little selection operation. That's going to look like this. So multiply and then select. So we only ask here the rows where for every row, just look and see, is this equal to this? The answer is yes, give it, otherwise delete. So delete, keep, keep rather, 125, keep. Delete, keep, delete, keep, because 125 sold 2 cars. You see how that works, right? Delete. Only when things match, keep, otherwise delete, which is how you will exactly end up with that result. And this is okay that you're in there twice, because it means you sold 2 cars. This is all still unique. It'll gradually become unique pretty soon, right? So that already filtered out this, the inessentials, meaning this and this cannot be different. They've got to be the same. So now the last operation is you tell the system, throw away one of the column names and rename it back to agent code. That is the projection operation. And then you're back to saying agent code. And now that's what the manager wanted. And then the manager can do a count and visually look at it and say, wow, who occurs many times. The Agent 333, I think, got lucky because you see that agent is now basically like, flying under the radar because that agent's number did not come up here at all. Okay. So in a standard natural join, you don't know who is like being inefficient. This makes all these agents look good, but there's a bad agent who's not even here. That is what the outer join is about to expose. So I'm going to show you outer join. But anyway, this is the result that you wanted. We can get a join operation going by doing a product followed by select followed by a project. Cool, right? Wow. Okay, so left outer join. Left outer join means go to my customer table and then output a value for every customer that there is. Output every customer. Even if the customer was sold a car that doesn't even work in the dealership anymore. Okay, so meaning there might be some number here, such as 421. That's not even here. I want to see what such numbers are. Like who are the customers, who unfortunately cannot get help from car salespeople that sold them the car because that salesperson left. So who are such customers? Maybe we should assign them somebody else. You do a left outer join. So left outer join says outputs all of the rows of the customer table. You will get your full customer table, including ones for which there are no matching values in the join column. In other words, 125 has 125, 125 has 125, 167. These are all good, but look at this one. There's no 421. There's a hole there. That's what left outer join does. Left outer join potentially has null values on the right-hand side. Conversely, our bad salesperson is going to happen. The right outer join will have a value for every single car salesperson, even if a salesperson did not sell to any customer. So in a right outer join, you will have holes on the left-hand side. In a full outer join, you will have holes on the left-hand side and right-hand side. Wow. How about you never thought about all this? All right, so right outer join, I want to read all this. You see, like right there. That person should be fired, unfortunately. Let go, given a warning, right? In 6 months, better sell one more car or else. Because you see, they've all been productive. This person has not been productive. You can expose that with a right outer join. A full outer join is actually both of them. It means you put the left and right together. Then you will have salespeople that did not sell cars to anybody, or customers that don't have a working salesperson anymore. It's the full outer join. That's an exercise. You can do it yourself, okay? So see what that looks like. So then you will have a union of both the right and left. It means you will see the customer that had like no car. You'll see this. You will see Smithson's name with nothing on the right-hand side. And you will also have ID 333 with like nobody to sell to. That is a full outer join. So union. Okay. Well, like, somewhat behind, but not too behind. So somebody asked me something. Yeah, I already answered that. Divide. What the heck is divide? Divide is so strange. First of all, you divide A by B, numerator over denominator. Numerator must have 2 columns. Denominator must have 1 column. Why do we get 5? Because that's what this is. Okay, so when you divide A by B, this column, first of all, should already exist here. It can be scrambled. You can have lock space code or code space lock. But then what it is A has a 5, B also has a 5. So take everybody here and go and see when they occur, who is common to this and to this. So 5 is common to A and B. In other words, it's an A5 and a B5. Supposing B5 was not there, the division would have a null result, okay? Because there's nobody that is matching A and B. On the other hand, suppose there was an F5, then in this case, A, B, if you divide the whole table, A, B like that, then you will still get 5 because A has a 5, B has 5. All we're asking is, like who is common to A and B. Suppose you have an F5 and then you have F here as well. Then you can say what value matches for A and B and F, then you will get the 5 back, okay? So it's all based on how this is distributed and who else occurs here. If you put F now, right now, there's nobody. First of all, there's no F here. Even if there was an F, say there was an F6, then you will get a null result. Because you have to match A and B and F, if I had an F here. So in other words, whatever is here, how many ever are here, you want matching value or matching values even. How would that work? What if I had an A6 and a B6 right now, okay? So we don't have that. But suppose you have an A6 and a B6. Then 6 matches A and B. 5 also matches A and B. So this can have one more 6 on the bottom. Okay? So it's all about who matches everybody that is in the divisor. Wow. Why did Card think of this? What the heck? One answer might be he thought, hey, we're doing union, intersection, difference, all that. We're doing multiplication. Might as well do a division. But division has very interesting uses. I want you to think about why or where you would use divide, okay? It has real world applications. And surprisingly, no SQL command for it. I do want to finish you guys, okay? We're like a little more than 100 bits, okay? So a dictionary. It's an entirely different idea from any of these, okay? All of these are so cool. They're all relational algebra. But a dictionary is just simply metadata. Somewhere in the system, you need to hold information about the columns themselves, not the actual data. Anything that is not data is called metadata. So again, if we erase this, you need all sorts of information the SQL engine needs to do very fast calculations for you. All of those operations, all of those data, they're called metadata. What if there are duplicates? Then I think the division operation is not defined. Yeah, that's a very good question. The dividend, I think, should have unique occurrences. That's a great question. Yeah, then such a table is not considered a unique table. We'll make sure that the dividend is unique, okay? Yeah. Think of dividend as people. Say the employees' names, okay? Or they are programming languages like C, C++, Java. You're trying to find out something about the top table, given that bottom table. So it doesn't make sense to repeat it, okay? That's all. But yes, I guess it would be real, but then somebody would have to throw it out. Cool. Like, if the bottom was C++ and Java, I can literally say of all my employees, who programs in C++ and Java. That is actually the answer. Wow, cool. Now I can go in my database and find out people that speak more than one human language, people that can work on more than one front-end, framework. All that I can find out. People who lived in more than one country. I can find out everything by dividing. Wow. All right, so a dictionary is just simply this. You have a table here, a different table here. Tables have column names. And columns have data types. Maybe this is an integer column, but only a 16-bit integer. This is a 32-bit integer, can hold like more data, but 32 bits. This one is like a string column that has 10 characters max. So the point is, even if you leave out your actual data, which is really what you operate on, you have other things that the system needs to know. Even things like how many rows does this table have? How many students are at USC? For each student, how many columns are we collecting? And for each column, what is the column name and type? That's like declaring in a class, having J, having a complex number, like Y or something. All of that knowledge without the actual data, right? 4 plus 6J. I'll do 6J. Okay, so leave the data out. All this extra information, even column names, column types, are all called metadata. Or even things like number of rows, number of columns, or even number of tables. My whole entity relationship diagram. How many entities do I have? How many joins do I have to make potentially? Is it hundreds? Is it just 10? All that is called metadata. The place where you store all the data, metadata, is called a data dictionary, sometimes called a system catalog. Very little difference between all these. I don't even bother differentiating them because they're all not actual data. Anything that is not actual data, there's still more data you have to have. Let's loosely call all of them metadata. And the place where they're kept, let's call them dictionaries, that's all. Okay, so data dictionary, system catalog. Homonyms and synonyms. This is simply, again, about column names. If you want to have a student ID and a student ID, conceptually, meaning logically, you want them to be the same thing. Don't call this SID, don't call this 2ID. That's confusion, right? So same name used to label, and then so that's what this was, synonym. So don't use synonyms. So STID, STUID was a synonym. And unless somebody knows it's a synonym, things will fail. Conversely, don't do this other horrible thing here either. Here SID means student ID. And here SID means sports ID. Don't ever do that. Because then somebody would think they're the same thing and all kinds of horrible things will happen. So don't use the same column name for two different purposes. Conversely, for the same purpose, don't use two different column names. Okay, so don't do homonyms, don't do synonyms. That's all. Easy. So, data dictionary meta, all this, just FYI for you. System catalog in dictionary, you can read more about everything. Tutorial Cup is a nice site. So like all kinds of DB entries and so on. Okay, so you can just read all. I skipped past all this, okay, but it's loosely what I told you, like that. It even has how many users use it. It's got like all kinds of information, because eventually the SQL engine, who which is tasked with giving you information, your results as fast as possible, can make use of metadata to tune your query, to actually recompile your query, and then give you results pretty fast, like this. Even names, UI cluster, DB tables. These are just IBM details, so ignore it. It varies by implementation, but the idea is none of this is actual data. None of this is your transcript data, for example. It's data about tables, really. We call them dictionaries. So that was a crazy, a little bit slowed down, but it's still a speed tour through the world of operators. Just neat. All these operations you fully understand, and nothing was particularly difficult, okay? They all exist for a reason. In Cord's paper, he names all of them and he has mathematical symbols for them. That's why he calls it an algebra. But what we take from the algebra is it obeys closure properties. Every one of them, table in, table out, or tables in, table out. It was not table in, complex number out. If you do that, closure would break. Then you cannot chain the operations. But he made sure that you can chain the meaning past objects around from operation to operation. Then you can make data science pipelines. These days you can visually draw them. Okay, we're at a point when you can actually go in a system and then visually draw, meaning you have a column here, and then it says words like select, project, union, intersection, difference. I can drag the select operation, drop it here, and then I can drag a project operation, drop it here, and then double click on it, and then read like a table's name, and then fill like what to select. Double click here, fill a different table's name, what to project. Then I can combine them by dragging a union operation visually, and visually I can wire them together. It's called data flow. It's one of the most favorite things in my world, meaning in computer graphics, we can use data flow for doing anything in the world. This can be image processing operations, there can be sound filters, there can be video editors. It's a great, great, great way to do content. But now you can do data operations by visually connecting them together. And then you save this graph. Next time you load your scene, this graph would just show up. And anyone that reads the graph, they can see like what you're trying to do. It's self-documenting. On the other hand, if I had none of this, I do all operations based on like file view menus, and I give you some result. You have no idea how I got the result. After a year, you would forget what you did. But in data flow, the graph is self-documenting. Anybody would always know exactly what you did, and you can start modifying it. Okay, it's a great idea. Anyway, that is possible strictly because of type matching. And Clojure automatically provides type match. No need to change any other type whatsoever. Just simply table in, table out, table in. Easy, right? Some of them you have to read from disk to start. Those are the leaf nodes. So leaf nodes go in the graph for the first time, and then it's a tree really. And the tree doesn't have to have one root. I can end up with two different results. In data flow, anything is possible. The only thing not possible in data flow is you cannot have a cycle. You cannot do all these crazy operations, right? So imagine you're doing these operations. An operation like that, and then combine this with something else. So you can just keep chaining forever and ever and ever. And something magical comes out here, right? You cannot then take the table and then turn it back here. Then you will get an infinite loop. It's actually possible to handle those, okay? But they're very hard to handle. So when you don't have a cyclical graph, it's called a directed acyclical graph. Acyclical means no cycle. Directed means you have arrows, okay? You're not going both ways. So a data flow is usually a directed acyclical graph. Even just a simple operation is a directed acyclical graph. Let's combine them. Okay. So we've done that. And then we can move on and do a little bit more. Then we can take a break at about 7:30, okay? Let's see what else we can do. This is now really what I should be talking about. Except this is very simple. This whole extended ER diagram idea is pretty neat. So ER diagrams you already know. You connect entities with primary keys, foreign keys, and they have one-to-one, one-to-many, many mapping. It's easy. But then you can think of some situations where it'll be great if your diagrams have a little bit more power. Like I can draw diagrams that express a little more. Specifically what you're thinking is, supposing I have a table here, and there's lots of columns to store some information about that table. You also have a second table here, It also has lots of columns to store information about the table. And then I'll make just one more. A table, lots of rows, more rows maybe, different number of rows. I call all of these pilots, okay, pilots, because it's an airline system. And every pilot has a row here, pilots only. So we call these mechanics, mechanics. Everybody that fixes airplanes, they're here. There are more mechanics than pilots, which is fine. And then these are the accountants that actually bring money to, the whole airlines company. Accountants, well, lots of accountants, like that. And then you can have marketing managers, all that. But the thing is, you look at the column names and they repeat. Social security number, because it's US Airlines, United Airlines. Last name, first name, date of birth, salary, spouse name, number of dependents, social security number, last name, first name, salary, spouse, how many dependents. Same thing. Social security number, last name, first name, right? Salary, when you join the company, all the same information. So you think, wow, these columns are all common. If you write 3 classes like this in image processing, X resolution, Y resolution, how big do you want my image to be? It's a blur filter, it blurs my images. This is a sharpen filter, also X resolution, Y resolution. This is an edge detection filter, also X resolution, Y resolution. You think, wow, I'm repeating members over and over. So an object orientation person would come and tell you, make a superclass and move the common values here. And then just simply make those others subclass from you. Now I can have a superclass called image class. I can subclass a blur from image, and the blur will not have resolution because the resolution is stored here. Blur can have blur radius. Sharpening can have an amount of sharpening. And edge detection can have an edge strength or something. So the whole point is these tables can be simplified by taking what is common to all the tables and putting them in one place and make like a super table. And then telling all the other tables, you guys are all like subclassing. And what links to all of them is simply employee ID. Every employee, whether they're here or here or here, has a unique ID. And only that should go here. So then in the pilot table, then it's a pointer. In the pilot table, I can replace all this information with just an employee ID. So in a pilot called 5, I can go here and look up all the information about 5. Likewise, in the mechanics, I replace all of the repeating information now with just one same thing, employee ID. So a mechanic called 8. Here's 8. There's all the information. It's beautiful, right? Again, when you write code, not even superclass and subclassing, I have 3 different functions. So much code is identical. I should just simply replace them with just one common function and pass arguments, right? It's very similar. It's called refactoring. So you can refactor code. You can also refactor tables and make a superclass table, subclass table. In reality, there are no superclass tables, subclass tables. It's all done through, like one-to-one operation, right? Because one person here is going to be, connected to one person here. So these are real tables. You can actually make actual tables and then just simply conceptually imagine that you're joining them. So an ID here would tell you all about the person. I don't have to put it here. Then I can use my real columns for what pilots do. I can have a column that says, are you a fighter pilot? Yes or no, Boolean. Can you fly like long distance, flights? Can you do like freight hauling, meaning can you work for FedEx? Do you have some other certification, advanced certification? I can have all that pilot information. Mechanics, do they know 3D printing? Do they know CAD CAM? Are the ISO 9000 certified mechanics? Only mechanic information here, or the CPA? Do they know government regulations? Do they have this, what? Only things that are specific. Again, in class hierarchies, that's what you do. A superclass has information common to all the subclasses. A subclass will only have specialized information about the subclass. What makes you a pilot? What makes a mechanic? What makes a mechanic? Classic object-oriented class hierarchy construction. We can do that. Then we call it extended ER diagram. Such a diagram would be called ER diagram. Neat, right? I'll tell you one more thing. So when you start to subclass them, there's 2 very interesting possibilities. Actually 4 possibilities, but I'll tell you 2 right now. One is this. It's all based on business rules, these possibilities. Supposing you go back to your pilot table. These are now the employee table. It's a superclass table called employee. It's an employee ID. Employee's first name, last name, social security number, manager's name, how many years they've served at the airline. Anything that is common to every employee ever. When it's the birthday, we can send them a card. All of those are looked up by employee ID. So now you come to pilots here, right? Pilots. The only thing that is common to here and here is just employee ID, because a pilot here is assumed to be the whole pilot. And then pilots can have certification, all the pilot columns. These are the core pilot columns. And then I'll do the same for mechanic. I already told you this, but I'll tell you something a little different pretty soon. And then this is accountant. You can have marketing, you can have, facilities people, restaurant workers. A real airport has like all kinds of things going on, airlines. But employee ID, same thing. Again, they're all being subclassed from the same superclass. This all already told you. But now, say this is Southwest Airlines. Southwest is very cool. They're like pretty jovial, they treat the employees pretty well. So when someone goes to LinkedIn, finds a Southwest job, they go on the form and start to fill it. The form says, what do you want to apply for? There are two choices they can ask you. On the one hand, you have radio buttons that say pilot, mechanic, accountant. In a radio button, you push one button, the other buttons are gone, meaning they're mutually exclusive. You can only pick one, okay? Cannot be all three. Pick one. Today, what are you applying for? I'll consider you for it. Even though the person might actually know how to fix airplanes, and they can also know how to build their clients. So that's a good person who knows all of them, right? But then the system artificially says, sorry, you should specialize. Just tell me which you want to be today. That is a radio button, right? One at a time. That is one possibility. It means the employee ID, if they're here, they'll not be here at all. That is one possibility. A very different possibility, which probably Southwest does, is simple check boxes that says, check whatever you want. So then this person who's a jack of all trades, Jill of all trades, checks all of them. Then such a person, when they're hired, they'll show up here, here, and here. It's totally okay. That is so cool, right? That possibility. So no one says, these all should be like unique. You can share. If someone else comes in, they're a pilot and a mechanic, sure, they're not an accountant. Then they'll go here and go here, they won't go here. But that person, whether you look at them from here, or that same person. So everything still works, but you can have duplication. Duplication is called overlap. Overlap is when you can be in more than one. Disjoint is when you can only be in one. Say there are 10 tables, you'll only be in one table, okay? Disjoint. So disjoint, overlap, the opposites. Easy. Just one more concept. One more concept is, now it's not about tables and employees anymore. It's actually about these tables here. Do I really know forever and ever and ever that every employee at Southwest can only be one of these or some combinations? Meaning, do you think I'll have more job categories in the future? Most people would say yes. What about an R&D department? You never talked about marketing. You never talked about, HR. Like, what are the facilities maintenance people that sweep all the floors at night? What about, somebody else? What about, international agents? We don't have all of those. Wow. Okay, so my diagram I have right now is incomplete. That is one possibility. The other possibility is, I know forever and ever that, every student, for example, that enters USC, the student ID all goes here. There'll only be a grad student or there'll be an undergrad student. I know there's nobody else. Even if they are like a PDP student transitioning from undergrad to grad, I'll put them here and here maybe, and when they become a grad student, only put them here. I can guarantee you there's going to be nobody else. When we know that, that's a different kind of design, okay? You're 100% sure this will not be extended in the future, okay? So there are 4 cases then. In the one case, I know to extend, I know I'll extend or I'll not extend, okay? And then an employee can only be in one or an employee can be in all of them. So there are 4 possibilities. I'm going to show you diagrams. The diagrams will look like this. On the one hand, you have a circle, 1 line, disjoint. Circle, 2 lines, disjoint. Circle, 1 line, overlap. Circle, 2 lines, overlap. So these are the symbols we're going to see right now. Okay, it's a neat idea. Okay, so let's do it. Advanced data modeling. It's not advanced. It's all right here. This is not advanced, but the book calls it advanced. Okay, we'll just believe them. Okay, it's advanced. Whatever. All right. So we call this extended entity relationship model. So we call them ERD, ERM, right? Now we call an extra E, like double ERD, double ERM. They mean the same thing, or M&D. They're just a diagram that tells you this superclass of thingy, but with that extra facility. This is the only extra thing. Is it overlap disjoint? And then, so then what are these super types and subtypes? I already explained them to you. This is super type, subtype. Like one type of entity, another type of entity, joined by, like a common ID column usually. A generic entity. Generic means it holds information common to all of the subtypes, okay? Because you don't want to repeat these over and over. A subtype contains unique, these are opposites. So anything that is not generic, like, why would a mechanic, have to have a column that says, oh, you're a fighter pilot? It's weird, right? So that only has to go here. Like subclasses are specialized. It's called specialization. So those are the specialization columns that only make sense to, if you're a pilot. All right. So that is all, first of all, you would do this in the first place. Only when you notice, wow, I have so much common, I should pull them up. When your tables already look fine, like professors and students and departments, there's no need to do this, okay? For your homework, by the way, it might be possible that you could do this. And it's optional. It's a cool design. But it will not penalize you if you don't do it. In other words, think in your homework if this is possible. And if it is possible, try it. Okay. But then that is the criteria. If it is possible to, have the subtypes, then you do it. Otherwise, just leave it, okay? You can read all this at home. All right. So all that this again says is, the reason why you make a whole bunch of pilots is because something has to be different for each pilot, which means in that certification, you have a certification column, and you make the column for a reason, because not everybody is a fighter pilot. Yeah, definitely. The homework would be out by this weekend. Sure. And you will get about 7 to 10 days, okay? Yeah. All right. So the same thing is called a specialization hierarchy. Specialized means subclass. So you start with a class and then subclass. So just a couple more things, and then the rest of the slides can go really, really fast. What it is this. There's two other things I forgot to tell you right here. One is you can subclass this again. So pilots can further be divided into civilian pilots, military pilots. So only military pilots, they'll ask you, can you fly like an F-14? Can you fly, the latest B-2 bomber? Can you do this? Can you do that? Can you fly helicopters, Apache helicopters? Can you operate a drone? You should not ask a civilian pilot all of that. It doesn't make any sense. So in that sense, what I'm saying is the class hierarchy does not have to stop at just one level. You can have multiple levels if it makes sense. A civilian can be, again, domestic flights, long distance flights, freights, like FedEx, DHL. Keep going. But what, again, relates all of them is just like one simple column, okay? Just specializing. Again, try not to put too much here. If there's too much here, then you look for a way to extend them. Like in a class, classes should be unique. They should only have members and methods that make sense. When you have too many members and too many methods, time to break it up. Maybe not even like this. Maybe make them two different classes if you want, but don't do too much, okay? Don't do too little, don't do too much. Right? It's called tight cohesion. Like within a class, all of the members and methods know each other. They love each other. And then you send a loose message to somebody else and say, you do this. So loose coupling. So tight cohesion, loose coupling. That is the magic of design, good design. All designs in the world have it. Even cars have this, not just software. In that sense, you can keep this going. The other thing I forgot to tell you is the whole dependence. What if there was a dependent entity called children and spouses or space? The whole thing that I told you, right? An employee can have many, children, usually only one spouse. The whole insurance table. That table is defined at this level because, everybody's an employee. In other words, every mechanic, every accountant, every pilot, every R&D, engineer is going to have healthcare, and so would their spouses, right? And so would their, children. Therefore, that relationship is assumed to carry through even for the children, meaning it means this person really, through here has children. So I don't need to bring that and stick it here as the whole point, okay? I can avoid doing this, relationship. If you define that at a superclass level, it is understood that subclasses also have them. Okay, so employees can have dependents. So that arrow stays right there, does not have to be here. But I can do something else that pilots can have a dependent table on, okay? It might be some equipment that, pilots know how to operate. But then that can be some kind of really cool dependent relationship, okay? And that relationship is also carried through because of this wire. So then this pilot inherits this relationship, inherits this dependency, and also inherits this dependency. So not only are class members and class methods inherited, but relationships between entities are also inherited. That is the main thing I want to tell you. So inheritance means two things. This is inherited by all the children. Also, this is inherited by all the children. So if you want to find a way to divide all of this into two parts, then those columns are inherited. Sorry, meaning those are like say this part goes here, and this part goes here. Then that name, is why you inherit like all of that. But then what I said was, if you make some new relationship that only holds for pilots, then for this and this are inherited. So it's as if you could draw this and draw this. It all makes sense, but you don't have to because you automatically get it. So someone had a question. Question said, or the subtype supertype similar to, yeah, 100%, 100%. Which is why when I talk about members and methods, I do mean subclass and superclass. So in object orientation, you do exactly the same thing. When you find writing many classes that have very similar functions and many similar data types, it's time to move them to a superclass and then just send them down and inherit them. So in object creation, that's actually what happens. So it'll make an object of this type. It'll also make an object of this type, Then when you run a method, there's a whole what's called virtual function table pointer thing that is set up. So the method that you run on this object, if the method is already overridden, meaning the method is directly available on the object, that method is going to be run. If the method is not available on this object, you say o.m, and if m is not defined here, then the system automatically searches your subclass and sees if m is defined here. If m is also not defined here, it'll go all the way up to the top. Only when m is not anywhere, the compiler might say, I cannot compile this, okay? In other words, that's specialization. The more you override, the more you make it more and more specific. That is more important, okay? So same subclass, hierarchy. Likewise, when you say, o.x, for example, and x is not defined here, then it thinks x is probably defined here. Okay, not defined there either. X hopefully is defined over here. So members and methods can be passed down. And members are just, accessed. You can write them. And then methods can be overridden. So a function here can be changed by this, and then you can change it one more time. And the latest always wins, which makes sense. So exactly like programming, okay. Okay. All right, so then move on. And then now I can show you everything, and it's so easy. All right, so relationships are what those wires were. This little wire that we had, right? This dependence idea, that's inherited, okay? So in your relationship, okay, sorry, this is a subclass, superclass. So a subclass is a superclass. A pilot is an employee. A mechanic is also an employee. Again, in object orientation, this turns into a little programming thing. There are two ways in which you can create new classes, okay? The one way you can create a new class is you can subclass an existing class. So already a class is there. You can make a subclass. So subclass is called is a relationship because B is a type A. Everything in A, unless it is private, B will also get. So B is an A. Like every bus is a vehicle. Every person at USC is an employee. Every vegetable is food. Just on and on. The other way you can make a class is, in fact, you can even do it here. You can inherit. This is also called inheriting. You inherit A, get B. You can also do what is called composition. You can take some other class, some class C, and make an object of type C within B. I can declare like a member of type C. There's no connection between them except I make an object and I stick it here. That is called composition. I put one thing inside one other thing. Like in a car engine class, you would compose it with a battery class and a radiator class, an actual cylinder, class and so on. Okay? A windshield wiper, mechanism class. They're all being composed because the engine is not some kind of subclass of, the cylinder or something. It's all weird. You just simply put things inside each other. That is called composition. Whereas here, what we're talking about is this relationship it's called inheritance, not composition. All right. So a subtype can only exist when a supertype exists. It's all true in object orientation. When there's no employee, there's no pilot. That makes obviously sense. And every subtype must have a supertype. This is not multiple inheritance, by the way. Okay. Although after the break, I'll show you exactly that. It is possible to make this multiple inheritance as well, which is so weirdly cool. Right now, think of as Java. Java only has single inheritance. You cannot have more than one parent. So it's just one compile. You cannot say class public : B, C. Literally one compile, okay? So you can make a new class called B by overriding, by deriving from C, but not D. In C++, this would work. In Java, this wouldn't work. You can try it. Okay. You cannot say extends, A, B, okay? All right, but in C++ you can. Okay, so that, and then the converse is obviously always true. A supertype will have multiple children because it has things common to all the children. Yeah, sure. That's funny, right? So the Java's workaround to not have multiple inheritance is to do what's called interface. You can say extends A, comma, implements B, C, D, E, F, but that's not what we talk about here. Okay? Yeah, we think there's only one. All right, so the diagram makes 100% sense to you. I spent so much time explaining it. Here's a pilot employee class. All the things that are common to pilot, mechanic, and accountant are all here. The main thing is the employee ID, because that is what's common to here and here. In here, literally ties all of them together. Okay, so when they were hired, what is the salary? What is the manager's name? You can put them all at the top. The top employee, all these employees, they have a relationship with a dependent child. This can be strong or weak entity, okay, it doesn't matter, but it's a dependent entity. This cannot exist if this didn't exist. You know all this from a past class. Okay, so an employee can have many children. Cool, super type. But now come to the subtype. Pilot subtype. What are things only pilots have? Pilot license class. What is your rating? Some other type. Medic type, medical certification. Can a pilot evacuate, wounded soldiers, dead soldiers, stuff like that. A mechanic, again, the mechanic certification title. Can you do advanced CAD? Can you program a CNC machine? All that goes here. Things only mechanics are hired for. Accountants, only things that, when I say last CPA certification, do you know, like the SEC's rules, to do business with the government, all that goes here. But then there's this very cool little thing here that says D. D means distinct. It means if an employee 5 here was there, you cannot have a 5 here or here. Distinct. And 5 is obviously going to be here. It means only one of them will have a pointer to a superclass. Like this can point to only one, so to speak. It's called distinct. If I make it overlap means 5 can be here and possibly here and even here, all 3. There's no what is called partition. When you have D, it's called partition, which means all the employees here are divided into employees here and here and there. Disjoint means you cannot do more than one thing. Okay, disjoint means you can only be this or this or this. Okay, disjoint. Simply a business rule. If the business rule is, like say a student can only be a grad student or undergrad student, or a student can only be a student, employee can only be an employee. It cannot be both. Suppose USA has a rule like that. All student workers will lose their jobs. Okay. Conversely, overlap means you can be this or you can be that. So those are the two opposites. Just business rules. Okay. So disjoint means only one. Disjoint means in reality, if this was 1,000 employees, maybe it's divided into 400, 300, 300, because nobody can be in more than one. Okay. That's what disjoint is. Overlap means that sum that I told you will not apply. When you have 1,000 people, in the worst case, everybody that ever works there can do all 3. So the 1,000 would be here and here and here. When you add the number of rows together, you'll have 3,000. That's one extreme. On the other extreme, all the 1,000 people can only do one thing. Then this can be split into 1,000. 3, 3, 3, 3, 3, 3, 3, 3, 4, something like that. Okay? Disjoint is that. Okay, so it's pretty simple. Inheritance, again, all of the attributes, which is column names, and all the relations such as dependence will be inherited. Yeah, I'm going to tell you. So complete means I know all my subclasses. So complete means in these airlines, I cannot make another table ever. Partial means I leave it open for the future to add more subclasses. Partial will have 1 line. Complete will have 2 lines. So the 4 possibilities are partial D, partial O, complete D, complete O. Molly, makes sense? Cool. Okay, so when you inherit the column names and also the relationships. Okay, and then so it's a 1-to-1 relationship, meaning for any one table, such as a pilot, the pilot's name would occur only one time in the employee table because it's a primary key really. So there's a 1-to-1 relationship between each table and its parent. That's pretty obvious in a way. And then the subtypes inherit all the relationships with children. So when the employee table has children, it means pilots have children, mechanics have children. Obviously, what else would you have? That's all. So it's one more way of saying all of this last line. Lower level subtypes inherit all the attributes relations from upper level. The levels can keep going. And relations can also be done at any level, at the top, in the middle, and the bottom. Just common sense, okay? They're all being passed down, okay? That's all. Nothing is passed up. Hand-me-downs, that's what it is. Okay, so this is the one that says, can I have overlaps? Can I not have overlaps? Can a subtype entry be in one table only one table, or can it be in more than one? Like, can I be only a pilot, or can I be a pilot and accountant? That is called a subtype discriminator. The reason why we say this is there's something very interesting. We go in the super type and have a column, okay? Okay. This will only work when we have disjoints. So supposing the airline says, when you fill in the form, you got to pick from a drop down. You can only pick one, obviously. So you put D here. At the superclass level, I make one extra column in my table. That column is going to have a single letter. So one character column. It doesn't take too much memory. That letter can be P or M or A, okay? And that should be enough to tell me what that employee is. So now this is the employee table. All employees are unique. Employees have IDs. But there's one thing called subtype discriminator, a big job description. Doesn't matter what you call the column, okay? But you know that there's a pilot here, there's a mechanic here, and there's an accounting table here. And we said D. D means disjoint. And it doesn't matter, you know, one or two, it doesn't matter. But then disjoint is what is more important. It means somebody can only be here or here or here. So then, supposing employee number 5 joins the company, and employee 5 is an accountant. All I have to do is say A here, okay? And that means that 5 is going to be found here. Employee 20 is a pilot. That means if I scan all of these, then I should be able to go to P and find somebody called P with 20 ID and find all the information. So that is all I need. I need only one column with one letter if D is true. On the other hand, suppose I make it O, okay? O means 20 can be here and 20 can possibly be here as well. So then how would you, at the superclass level, handle it? Look, what can you do here to make note of the fact that somebody can be in more than, you know, one? They can be all 2 or all 3. 2 means they can be PM or MA, or they can be, you know, AP or PMA. How would you handle it? Look, what can you do here? It's almost like the discussions are starting, okay? So I'm actually asking you questions. Yeah, another column, sure. So tell me what the column would do. That's one answer. There's actually 2 different answers. Oh, I like that. You're 100 coding, exactly. Yeah, so 3 columns is the other answer. So between Hamza and Molly, right, they're both correct, okay? So let's do Hamza first, because she mentioned it. What do you do in the column, Hamza? How are you able to say that somebody is a pilot and a mechanic? What can you do here? Just be creative, okay? There's not like one right answer. You can get away by doing so many things. No, not really. See, that won't work, right? Because I want to say that the person can be a pilot and a mechanic. So just to be practical, how, like, what would you say there to say that they're pilot and mechanic? So 3 bits. Okay, so a different answer would be, you still have what you had, right? It's what Molly said. You can have 3 columns. 3 columns. These are 2 different answers. You can do it 1 column, or a different designer can actually do 3 columns. So if you do just one column, what would you put there? Okay, so forget 3 columns. 1 for true or false. True or false for what, though? Take a practical example. You know, I'm a pilot and mechanic, but I'm not an accountant. So how would you specify that here? A single bit is not enough. The column can only hold one thing, by the way. A column can hold only one cell. Yeah, exactly. You can start doing strings, right? What if I do a string that says PM? And I just parse the string. If it's got 2 characters, I see what the characters are. That's an easy way to cheat, right? If somebody is all 3, I call them PMA. It's a string encoding. Yeah, you can encode however the hell you want. Exactly. See, now you're getting pretty smart. How would you do that? That's a damn good answer. What would be the integer? One CG to answer. You're right. Combinations, exactly. What if I had a pre-done combination that said 0, 0, 0, which is, you know, decimal 0, is a pilot only, you know, simple pilot. So enumerate all possibilities, okay? So 0, 0, 0 is P only. PM is, you know, 0, 1, 0. No, it's like number 1. And then 0, 0, 0, 1 is number 1. And then 0, 1, 0 is number 2. And then 0, 1, 1 is number 3, okay? I'm just going to enumerate all of them up to 1, 1, 1, and I'm going to call that number 7, okay? So this ID can actually go over here. So if this says, for example, you know, the number 4, then that means 1, 1, 0. So they're pilot, mechanic, not accountant. Makes sense, right? Yeah, sure. You know, you can do it in many different ways, you guys. That is the point. But the cool thing is you answered many of them. So I would go with strings. I would go with some kind of a really cool integer. They're all possible. For that matter, you can even do, maybe somebody mentioned this, you can even do the whole bits right there. You can even do that. Then I can say, that is like, 6, right? Yeah, so you can get away with lots and lots of things. Or you can do it this way. Here it's a strict Boolean, pilot, yes, no, mechanic, yes, no, accountant, yes, no. So I have to set individual bits on and off. Pilot, yes, mechanic, yes, accountant, no. It's possible to do it like this as well. Okay, so think about all these implementation alternatives. Okay, it's fascinating. All right, good. This is great. We should take a break because heads are heating up and saying, "I want to go to the bathroom." Yeah, exactly. Damn smart. Depending on what you do, you might do very little processing or more processing. Okay, so just pick your status. Thank you. I appreciate it. So it's always a trade-off between the computation and memory, of some kind. This wastes more memory, right? Like 3 different columns, but instantly you'll know. If the query says pick all the pilots, this is like really simple. The query says pick all pilots. You have to do like a one-level indirection, right? And look through this table. So because remember this is in the main table. This I glue on 3 columns and I directly make them ones or zeros. So very fast, easy to query. Yeah, but a little bit more save space if you do it the other way. All right, so take a break from like 7:36 to 7:46, and then we'll just continue. Okay. So I'll be back in 10 minutes, you guys. Bye. All right. Back already? Here, continue. Something changed. Hey, wait, the background changed. There's a little trapeze artist going, wee! Look. Yeah, look, this little character.
You drew this?
Can you hear me?
Did you draw this?
Yeah, I drew that, yes.
Wow. That's a nice drawing.
Oh, thank you so much. It looks like Cirque du Soleil, right? With trapeze artists and people with like costumes and things. No animals. It's a human circus. Cool. Okay, so what I wanted to do is tell you a little bit more, right? There's not too much more, and then that way the discussions can be more meaningful because I have some neat things to tell you. Then we'll have a nice stopping point. But the main idea was just what we talked about, which was I can have extra column or columns to take care of the disjoint possibility or the overlapping possibility. So nothing is a problem. You can just design your way out of things. When you have more subclasses coming in the future, and you would leave this with one line, it's called a partial constraint. It's funny they call it a constraint, just a partial subclass, list is really what it is. When you say a complete or a total constraint, you draw two lines. That means in the future, there's no possibility to add one more. So your table design can be locked down in terms of how many columns you put in there. That's all. So therefore, just some extra examples to illustrate those. This is where we were. So the one column at the top that says P or D or M, they call it the subtype discriminator column. When you have multiple columns, that columns have no name. They're just binary pilot, yes, no, mechanic, yes, no. Okay, so then disjoint overlapping. This is what I just now said. Disjoint subtypes means contains a unique subset. It means I can break my employee parent into partitions, meaning number of pilots plus number of mechanics plus number of accountants will hopefully be the employee. So those are called non-overlapping subtypes. And then it's a partition. It simply subdivides your total. On the other hand, overlapping subtypes means I can be in more than one table. So then the numbers don't make any sense. In the worst case, the numbers would add up to the employee. In the best case, the numbers would add up to the number of employees times the number of tables. I can be in every one of them. Okay, in between is in between. All right, so that's all. And then here it says when you have overlapping, when you can be in more than one, the wasteful way to do it is make a Boolean column for each one of them. Are you a pilot? Yes, no. Are you a researcher? Yes, no. Are you a marketing department? Genius? Yes, no. So then you can make a column for each, or we can cheat and have strings. We can use like an enumerator to point to a different table. You can do many different things. Not an issue. And so when you can overlap, when it can be in more than one, then we use two lines. And this is a different example. Suppose it's USC. Everybody is a person. We all have an ID, like an employee ID, student ID. And then you have this Boolean column that says, are you an employee or are you a student? In my case, yes, employee, no student. In your case, it might be, yes, student, no employee, or a student worker, one of my CPs would be both. So we give that possibility by saying, O means overlap. It means you can be either here, or even both. So an ID called 5 can be an employee, 5 can be a student, 5 can be here. That's totally okay. That is an overlapping constraint. And then you can divide further. So now you have a 2-level hierarchy. Okay, you're an employee, and then you can only be, so the employee does not subdivide into too many possibilities. Everyone, just imagine, is either an administrator or they're a professor. Just imagine the school does nothing else. So then you can be either one of those. Actually, wait, sorry. For now, when you're hired, you can be an employee, you can be a professor, and you can also be an administrator, because that is what Dean Yanis Yordas is. That is what Professor Cyrus Shahabi is. You can be the head of the department, and you can be a professor. In my case, I'm only one. I'm not the other, but I could be if I qualify. That's what the O says. The single line says, these are not the only things people do at USC. What about research administration? What about sports? What about librarians? What about other people? What about what? So all of those are a single line. It means I can have more in the future. But look here, though. So this one is basically the opposite of this. This one says a student. So first of all, you can be a student worker. That's good. You're paid. But now a student has to pick. You have to be an undergrad or grad. If you're a PDP, I'll make you one. Just pick one. What do you want to be today? At some point, you will make a hard transition. And the second double line is more interesting. It means there's no possibility to change this in the future. Okay, so students, when they come in, there'll be a grad or undergrad forever, and we don't have a third or fourth. That is what double lines mean. So now you've seen an example of all four types, okay? You've seen double lines on the bottom, single line, and also single line over here. And I had that single line with that line. So this is one of the examples. And then the other three types are all here. Three types are all here. So you can study it, okay, to make sense. That's all. And then, so when you don't have any more to add in the future, when you say a student can only be this or this, then we call it a total complete. These are all weird words, by the way. This is almost an oxymoron, like jumbo shrimp or something, right? The words don't belong together. Partial complete, what does it even mean? Partial complete, partial subcategories, total subcategories, that's all it is. So partial subcategory would be this partial completeness, because I did not add the bulk of what people do at USC. And then in the students, on the other hand, nothing more to add. That's called total completeness. So partially complete and total complete, okay? Single line on the bottom or double line on the bottom, really easy. So you can read this, I'll absolutely not read it at all, because that is what this says. Again, D, D, O, O, single line, double line, all four possibilities are covered, and that's all there is. Easy. And then, this is just for fun. This is a very different, again, concept, and we can stop. This concept has nothing to do with EERD at all. You're going back to ERD, or you could do this for ERD as well. It is simply a visual collapse. So what if, like at the end of last lecture, we put all the whole ER diagram together. It had many entities, maybe 30, 40 entities. In the real world, you might have 200 entities. So the diagram becomes like so complicated. And then somebody says, the academic unit says, I only want to see these tables. Can you just hide them? So wouldn't it be nice if I can curtain drag, right? Just do a little curtain drag. And then I just click and they all hide. I sweep them under the carpet. And I can put a little name there that says facilities management or something. That is what this is. When you do that, it's called an entity cluster. I can grab a whole bunch of entities with all their wires and call them something. The key is I'm not making a new table or making them subclasses, nothing like that at all. It is purely visual. It means when I double click on this, it'll open up and you will see your original diagram, okay? So please don't think these are new tables that absorb the old tables. It's all like confusing. That doesn't happen. It just means visually hide because it is too complicated. All I can show you is a new compositing graph. It's like DreamWorks. So compositing is where you take tiny pieces of images from all over and then put all the pixels on top of each other, next to each other, and make a very cool image you see on your big screen in the movies. You would see that. In reality, that was a separate image. And then this was a separate image. The background, which is blurred, is a separate image. So you can make an image in the screen. That's a separate image, from tens of thousands, believe it or not, if you want tiny pieces of images. And we have a graph, in fact, a data flow graph, like I told you earlier. That graph can look crazy. So, visual effects supervisors want to understand the graph. Turn it off. Just show me only this part. What the fuck is that? They get angry, right? So much. So you want to collapse them. That's what these are. So these are entity clusters, okay? So you can visually collapse them and somebody could click on it. It'll all just disappear, okay? So way to just hide and group things, that's all. But no real grouping is actually happening. All the colors that you see, you can leave little comments there, It basically means don't look at it. Because the graphs can actually be hellish. A digital domain graphs had thousands of nodes. It means each frame in Titanic came from literally thousands of mini little pictures. Because James Cameron, who directed Titanic, was a perfectionist guy, and he had a foul mouth too. So look at a screen like that and go, "What the fuck is that on his forehead?" "Oh, that's a tattoo. Get the fuck rid of it." That's what he would say and walk away. And some poor artist would have to go find the node that actually has it on and turn it off, and then render the whole thing over again. So we keep it all separate, okay? So node graphs from hell, you can search through them. There's a lot. I'll just one last time, just a node graph from hell. So these can, be quite complicated. Look at that. Oh my God. So, somebody understands all this, and somebody's job is on the line if you don't know how to fix it. Therefore, collapsing them visually is the only solution. Oh my God. Man. So the data flow is that complex, input images get fed in, and finally your movie appears. Look over there. OMFG. That's what this is, okay? Just ignore it. Double click on it. Okay, so that was a fun little tour through the world of extending this notation. It's all just to make the notation look very nice. When you look at it, the columns, are very simple. because they're assumed to have this, one-to-one relationship with your child. And then you can make your designs look more expressive. That's all, okay? So when somebody looks at the column, the names is this only in one. Imagine all of this repeated over and over. It looks ugly. So that's the sole reason why you do this. Otherwise, at the database level, there's no extra things we glue on. The SQL is still all the same SQL. Nothing changed. Beautiful. So with all this out of the way, next 20 minutes, I can have you answer some questions for me. We'll definitely talk about closure. And then this other thing that I talked about, which was you can have this single inheritance, which we just saw, be actually multiple inheritance. You can actually flip the whole child-parent relationship, meaning a child table can actually inherit columns from multiple parent tables. Wow. It looks the opposite of, a single parent employee, pilots. So I'm going to show you that now. Where is it? There. Oops. So we can do this, right? And then it might take some time. And then afterwards, I can go back to closure. So we still have some lingering questions from here. We could do it in order, obviously, right? So like that one. But maybe we'll leave closure to another time, because what I'll show you now is actually a little bit more important than closure part of it. Closure is cool, but I think this is good. First of all, where else can you think of when you have a bunch of tables that all store data, like sibling tables, similar kind of data, and what can you abstract out of it? What do you think? It can be in any domain at all. It can be food, can be books, can be GPAs, can be grad students. But try not to repeat what we already had. So maybe not employees, maybe. But what else can you do? There are many places in the world where you can actually have subclasses, superclasses. Yeah. Oh man, these are good. You guys already, man, you're ahead of me. Yes, supermarket. So what would you do in a supermarket? That's a great answer. What kind of hierarchy would you have for things in the supermarket? Vehicles, yes. What hierarchy? Airport management, how? Products, yes. These are good. Good. What about health insurance? I guess you can cluster the types of things they insure. In a financial institution, yeah, this is a great one, okay? Yes, you can hold many kinds of so-called financial instruments. You can hold, assets of many types. You can have stocks, bonds, jewelry, real estate, and they can further be subdivided. System requirements. You need to explain what that means because I don't understand. Different categories. Are you talking about something that you went back up on? Different categories. Perishable items, exactly. Supermarket. In fact, on the wall, they actually write that. They go dairy, they go, perishables, groceries. Yeah, those are like super categories. Because in all the perishables, maybe they'll have separate things, just for the perishables. Maybe 2 different expiration dates. One, the real one that's actually stamped on the vegetable, and the other one that they secretly hold and put things on sale. So, in other words, basically it's like categorizing things in life, okay? The one thing that nobody mentioned is the life categorization, which came up a little while ago. Absolutely, sure. Yeah, this is actually very good. Like say you go to Office Depot, then they'll give you a different business account versus customers, and they'll treat you differently. So you can start by having all the people that are customers at Office Depot be business, and then they can be customers, like individuals. But something else about life that can have the most amazing extended hierarchy ever. What was it? Yeah, exactly. Taxonomy. Yes, you remember the Linnaeus taxonomy, right? The guy's taxonomy pretty much carries every single life form ever invented and the ones in the future. His taxonomy never had to be extended, okay? You can always find a place to plug anything that you ever discover in the world. Wow. So that's the ultimate, subtype, supertype hierarchy. There's many more, okay? Even the army, again, any soldier, right? All of their, things can actually go back higher. So like the soldier's ID at the very top, the dog tag would be at the very top, and then all get passed down. So there's lots of things in the world that can have more than, like one category, a tree. And to the extent that they have data in all those nodes, you can now start to make like ER taxonomies out of them. Okay, fantastic answer. Okay, so this we already talked about, just one more time. Overlapping, this one you can be more than one, okay? You can be PMA. So in the textbook, they gave you the worst way possible. They said, make 3 columns at the superclass level, Boolean, pilot, yes, no, mechanic, yes, no, candidate, yes, no. Then I said, how can you do a single column at the parent level? You guys had many answers, right? So one would be string. You can say string PMA and just parse it. Or you can have bits for them and have 110 and parse it. Or you can have a number 7, like an integer version of 111, and then break it down into binary, and then know that 111 means all the flags are turned on. So like maybe 3 different ways of storing information, all in just a single column. So then in B, how would you do this using a separate table along with the parent? Yeah. So then, say these are 2 different cases. How would you use a separate table? In other words, it is not oh, I'll tell you. So the book has the worst way possible, but if you do it yourself, you can still use 2 tables. So what would be the advantage of using 2 tables? That's the question.
Yeah, I guess I would just use voice because I can't type as fast.
Sure, yeah.
I think the way about using 2 tables is that if you just want to query all the possible options, then you could just query from the options table. So think about the options table as like a way of storing an enum of possible enum options. Like if I just want to get all the possible enum options, I can just do a select star on the options table, and I will be able to get the corresponding like the machine readable value and human readable value.
Yes.
And if I want to do so which basically means if I just want to query like options, for example, say like have an application form that says what do you want to apply, it's going to be a simple select statement,
right?
And it doesn't really, and I guess that's basically it's like simplicity. And if I want to query like pilot, if I want to query the actual human readable name, human readable like job description, I could do an inner join on both tables, and I could do an inner join on both. No, I could actually do a union on both tables, and I could then for the temporary table I could do another select which just excludes the machine readable columns, and I will be able to get a description of the name of pilots, their ID, and probably like also their job description.
Wow. That's a pretty detailed, really cool, super cool answer. Okay. The thing that I was asking though was actually a lot simpler, but I just love your answer because yours is a complete answer. If these are filled with data after all, then you're describing actually how to go and look for who are pilots and mechanics, right? It totally work. Okay. So my question, just to make it clear, is a much simpler question. So I'm going to ask you, what is the difference between doing something like this, right, versus having the columns right here? Okay. The book says just have a Boolean column called PMA. This is all for overlapping. Everything's for overlapping. So when somebody comes in, I can just turn them on and off. I can just do all of this, right? That's one way to do it. But then my question really, if you look at B, I asked you 2 questions. The first question that I asked was, how do you only use 1 column? And you said strings, and you call it that. But then if you do 2 tables rather, this is the way to do it, right? Because you list all the different enumerations, and then you can even number them from 0 to 7, right? And then I would just put, like instead of this, I would just have 1 column, and then basically it's a combination column. So if the column says 4, then I would know looking here that 4 means, because we don't know what order this is. Say 4 says 100, it means only pilot, no mechanic, no accountant. So my question really is, what is the difference between doing it like this versus doing like what the book says? So let's see what people said, okay? Easily extensible with new table, less storage for large data, so redundancy. Man, all of those are right answers. There's also a good answer. I mean, they're all great answers, okay? You have a new table that decodes. Yeah, sure. That's the only indirection. You have to lay indirection. What about wasted space to start with? Wasted space. Supposing there's more, okay? So there's also like 5 of them. So then in the book version, I have to make 5 Boolean columns, right? 5 Boolean columns. And fill for every employee 5 yeses and nos. Most employees only work for like one or 2 divisions, right? So all of these are just wasteful, okay? Say I have tens of thousands of employees. Then what is the difference between doing it like this versus doing it like that? Say I have 10,000, maybe 40,000 employees for Southwest. 5 columns versus one column. The big difference is what? Yeah, exactly. Well, you have to have another table, right? Actually, what I mean is, these are done only one time, right? Supposing there are 5 entries, then I would have the 5th value here, and this would just simply go up to 2 raised to 5. So then 31 would still be like all the ones, right? So this table just grows very simply. Every time you have a new column, this table length doubles. Only filled employees that are P, M, or A. So you guys are not giving me the actual like hardcore answer. So the difference is this. The difference is doing it like this with lots of columns versus only one column for the employee table, with the idea that I can always go and look up something here. So what big advantage does this provide versus that? Yeah, sure, you have to access all columns. That's not a problem. Okay, so imagine queries are fast. So because the proper answer is still like a little bit far away. You guys are a little cold now. I want to do it one more time. The difference is the question is, what if you do it this way with PMA being booleans? That's one way. Or what if you do it using 2 tables where the 8 possibilities for PMA all go here, 0, 0, 0 up to 1, 1, 1, with an enumeration that goes from 0 to 7. And I only have one column versus 3 columns. But 1 column and 2 tables required, because if I have 5, then I'll go look up 5 is 101. I know the person can also do tax, during tax season.
Yeah.
Less null values, correct. How can you say it better? But you're absolutely right. Readable, that's also true. There's something else. Add a new, yeah, exactly. So that is one good answer, right? If you add one more column, it is easy to update because you can just go and add like any number of things here, right? I can just keep retaining the one column that I have here. But that still all leads to one more advantage, the one last advantage, exactly, space saving. See, that's really what it is, okay? Because here, every time a new employee comes, right, I have all this wasted space. That is the big advantage. Here, I only have one column, no matter how many employees, because I made a table out of it. It's useless to repeat this information here over and over and over again. That is the big advantage. Do you understand? Yeah. Okay. So by doing it this way, it's always only one column because the column is like an encoded column. The column encodes what should be here. Whereas here, no encoding, you're just wasting a lot of space. That's the big answer, okay? But every one of your answers is correct. Okay, I love it. In the remaining minutes, though, I want to show you something new. Ha. Okay, so this is when you can have a new thing called a union subtype, okay? And something called a shared subtype. I'm going to give you one example for this, one example for this. A union subtype is you would use a union of supertypes and get one subclass like this. Wow, this is a new thing that we've never seen before. And then after that, this is pretty standard, okay? And then this is the second example. So in the first example, what is happening is, say California DMV wants to track, who owns all the cars, trucks, and helicopters and motorcycles and boats and everything, right? Then they have this database. But at the very top, this table called owner is a list of all the different people that own different vehicles. But the thing is, if you look around on the freeway, if somebody's driving something, a person can own that vehicle. Or the person took a bank loan for like $50,000 and got some kind of Mercedes, and they've not paid it back. So then the bank, until that time, owns the loan. You can even say temporarily, and the loan is being paid back. They both own it, okay? That's possible even, so it can be overlapping. Or some kind of car leasing company can even own those cars, okay? So therefore, the owner ID can come from here or here or here. Or even using multiple columns, some combination of them. Maybe all 3 of them can even have an owner. So in that sense, you have superclasses all leading to one subclass, like a multiple inheritance, okay? Like multiple inheritance. So multiple inheritance, we call it a union subtype, because a subtype can be a union of multiple supertypes. So cool, right? So that is for the owner part. And then you have then this is like a bridge table that for every owner. Also, so this is just who is the owner. Is the owner a bank or a person or a company? And depending on what they are, you can go and look up information about them. If the owner says the owner is a bank, then you can look at the bank's, ID, for example. If the owner is a person, you can go and look up the driver's license. So imagine a table of all the owners that ever own cars in California, okay? On the other hand, you have this owns table, this registered vehicle table, where you have another table for every car or truck actually on the road, it says what type is it? Is it a car or a truck? So there's an entry for that. And if it is a car, then how many, say how many engines and what is the, capacity of the car, what is the maximum speed, and then what is the make, all that for a car. For a truck, how many axles, how many wheels? Maybe trucks can be heavy. So the truck information, car information can actually be stored in for every single registered vehicle. And then this simply combines them. This says for every owner, because an owner can own many cars, right? Or a vehicle can have multiple owners even. So that's a many to many. So this part is like things you've seen before, okay? So don't be confused by this one. But this is the cool part where multiple super types can all, maybe one at a time or more than one at a time, lend their columns to a single owner. So this is called a union subtype because it's union subtype, a super types to make one subtype. It's a unioned subtype. So think about it. And then you can also have some, so you're subclassing from multiple, this is what I showed you. Or the next diagram, you can have something called a shared subtype. In a shared subtype also, you are subclassing from multiple supertypes, but there's one difference between this diagram and the next situation. So the situation I showed you with the cars is called union subtype. Next is called shared subtype. This is a shared subtype right here. And I'm going to ask you what is the difference. In a shared subtype, it starts like this. This part is pretty straightforward. Everybody who passes through USC can be an overlap between an employee, or they can leave USC. You're still a Trojan, right? You're an alumnus. And or you can be a student. If you're a student employee, there's an overlap between you. And maybe a student that just graduated, maybe a student alumnus. Or an employee, that worked and left, they're an employee alumnus. This is all cool, right? This part is pretty simple. But then now come the more fun part. And this is actually the more fun part. What happens is the employee can again be a distinct disjoint between a staff, faculty, a student, assistant. So anybody, that I work with would only have to be one of those. Like Lisa would be staff and I would be faculty, and my CP would be a student assistant. So this part is simply a standard disjoint. This part is also a very interesting standard disjoint. A student could only be a grad student, undergrad student. You cannot have high school students. You cannot have, postgraduates. You cannot have postdocs. Just pick one if you're a student. Okay, this is cool. And then you now go here. So this is where you're doing a shared subtype, okay, a shared subtype. You're sharing a subtype, and I'm going to come back to this in 1 minute. Shared subtype. A shared subtype is a student assistant. This is a shared subtype because you're sharing employee characteristics and also student characteristics. For example, you can have, employees like tax ID or something. You can have a student's GPA because student assistant is both an employee and also a student. And then this is pretty straightforward. If you're a student assistant, this is true for many schools in the country. We send like letters worldwide. It'll tell you have 50% TA, you have 20% RA. So a student assistant can only be one of these. They cannot work in the library. Okay, just make a rule like that. So grad students, for example, can only be this. So this part is pretty simple, but this part is very interesting right here. This versus there's 3 here, but just leave a third one out. Okay, imagine there's only 2 of them. There's still one difference between having 2 become 1 and having 2 become 1. What is the difference? Just look at it for a second. Think of a student assistant, being an employee, they're also a student. And then here we're saying the owner of a vehicle can legally be a person or bank or company. If you carefully hear me talk, I'm dropping all kinds of hints here.
I'm not sure if that's right, but the owner in the union subtype can only be one of the 3.
Okay, yes, okay.
But in a student researcher, in a student assistant case, you actually is an employee and so it's basically or versus and.
Pure answer, perfect. Yeah, good. So Shreya said the exact same thing. You guys should share the price. Yes, it is a difference between or and, believe it or not, okay? Here it has to be and. The columns here must actually relate to these and to these, whereas here it's actually an or. Wow, cool, right? That's the answer. Nice. Good. Okay. So now we can finish this for like 3 minutes, right? These are fun. These 2 little things are fun. I want to talk about normalization because we've not done that yet. Okay, this we can keep for next class. So very simply tell me, say this is Staples Center. Okay, Staples Center. given this bunch of data that they have for all the events that happen at the Staples Center, what could be a primary key column, or what combination could be a primary key column? Combination of room and event name, you know, event names can actually be like, you know, similar. What if all events are called birthdays? Date and event time, date and time, room start, time end. Time start. You know, time start, time end, the same. Many events can start and end at the same time, but they can happen in multiple rooms, so that wouldn't work. I would argue date, time start, time end room. Yeah, sure. So CG might be right? Because, you know, an event can only happen in one place, right? So just include all the details about the place and the time. Basically need the combination of everything that makes the time unique and the place unique, okay? Okay, but then the problem with that is, it's like a lot of data. It's like, you know, so much information to store, okay? So then conversely, what can you do? Okay, that would be a right answer. Have some combination of, you know, like place and time, okay? Yeah, you actually need place and time. So the proper answer would actually be place and time. Because at one place at one time, there's only one, you know, event can happen. But what is a much better alternative? What would Staples Center do? What if you design this table? What would you do for them? You would just simply make what? Like what other kind of primary key can you have? Yeah, a blind key, right? A 10-digit ID. It doesn't even have to be sequential. If you want, you can have sequential. The word index means a very different thing, Hamza. Okay, so I wouldn't use that word. Maybe you mean like a numerical, like 1, 2, 3, 4. Every time you add one more row, it's like a plus plus. And that's a good thing, because then you, in one glance, you can know, wow, I did not believe that we have 10,000 events this year. That's cool, right? Yeah, so a single ID would be much better than anything that we ever said. Having event name is a dangerous idea only because some events have very long names. So if you know you want to store the whole event name, you'll be wasting so much space. Conversely, if you cut it off, then many family could literally be the Smith family, right? So then the event names won't be distinct anymore when you're trying to do like analytics later on. So the short answer would be have a blind ID key. Okay, so we're running out of time, but I want to ask you just one last question. What about, so what is special about here? Like, what is this? Just look at this image. What are we looking at? Dental procedure codes. Meaning, I'm not asking you now like what they are, you almost know, but you know, just like say a few words about this. Like, what is all this? Why would we use this? Why would the dentist's office use it? Okay, I'll start by telling you, these are primary keys for all the different things that you go to a dentist for. So anytime you go to a dentist, say you want to have a little polish on your teeth, right? It's called an amalgam. One surface amalgam, D2140. They'll bill your insurance company by $1,000 for that. You want to do something more complicated, they're going to bill you $3,000, right? So then that is D2330. These are blind, basically, you know, because there's no sense and there's no meaning in them. They are primary keys for much more complicated sounding procedure names that people might not remember. Yes, it's for optimizing space because these are much simpler. They always have the same. There's not more than 10,000 procedures, so 4 digits are enough. And every insurance, you know, every dentist office, they share all of these. The whole dental industry shares these numbers. So in any, you know, insurance company or any dentist office, they would all know what 2330 looks like, right? That is all it is. So you would use it for all those reasons, to save space and also not have a data entry person type this by hand, God forbid, and forget the parentheses. Okay, then you wouldn't know what thing it is anymore. You can search for it. So blind keys are much, much easier and nicer than arbitrarily long medical names that only, you know, dental surgeons and dentists, you know, can remember. Cool, right? So if you look around in the real world, there's like so many things. That's why in the hospitals, you know, they have emergency codes, you know, again, very similar. Instantly people know what the code means because there's no time you until or cardiac arrest pressure, you know, it's a code blue. So that is what all that is for. So pilots have codes, you know, hospitals have codes. Many, many places in the world have these codes, and they have for a good reason. Cool. Okay, so I think this is a good way to stop. So when we come back, we have literally exactly normalization, okay? So I'm gonna do normalization, and maybe it's a good thing because this actually is a lot of SQL. So I might stop right there and then find a way to distribute all these, okay? In the end, we'll never lose anything. Nothing will get pushed off. We get everything done, all right? But next Wednesday, we're going to do normalization followed by this first type of SQL. In the meanwhile, you have enough, I think, to do your homework with ER diagrams and ER diagrams. So good luck on that. Okay. Goodbye, everybody. Bye.
Excuse me, Professor.
Yes.
I have a question.
Okay. By the way, then people can record or stop whenever they want. They're free to go. Our students, same thing. They can stay. You can ask a question. Go for it. You're welcome, everybody.
Whenever we delete an entry from a database,
Mhm.
so it should be deleted in the other database, right?
Correct.
Other entity.
Tables. You call
yeah.
the whole thing is called database tables. Right?
So isn't it a bad thing instead? As if we want to look at the historical data, for example, we need to plan the strategies after a year or what.
Mhm.
So isn't it a bad thing to delete that?
It is. You could argue both ways. Okay, I say yes. It depends on the business situation, but you ask a great question. Okay, I'm going to answer it. So I say this is the PK, okay, and then say this is the FK. So the problem always is what happens if the FK, is null. So there's a number here. 5 is missing. Question is right now when you come across this, what should you do is the question. One answer is you delete it. But if you delete this, then you lost all the analytics. You never know that a person called